Summit. However, please note that we can't guarantee all sessions will be included in these recordings. So with that, I've taken care of all the necessary housekeeping, and I will pass things over to Nathan for presenter and talk introductions to get us started through the technical program.
Okay, thank you, Caleb. Yeah, I'd like to introduce our first speaker. He's our keynote speaker for this morning. His presentation title is Applying Fixed-Wing UAV Geophysics to Resource Exploration and a few lessons learned. This is Markku Pirttijärvi. Take it away.
Hello, thanks. Let me share my screen first. So I hope you can see my screen.
Yep, we got it.
Good. Okay, hello everyone. I'm Markku Pirttijärvi from a Radai company from Oulu, and I'm here to talk about our experiences over the last few years on using fixed-wing drones on geophysics, mainly on magnetic surveying, but we'll go some other issues as well. So, few words about our company. It was established in 2013. We are located in Oulu in North Finland. We have a company of about 10 employees, and we have a partner, or actually a daughter company called Drone, which is performing our flight operations for us. And our main service is magnetic surveying. And typically we do something like 10,000 to 20,000 line kilometers per year nowadays. Optionally, we do provide 3-component XYZ component measurements and also 3D magnetic inversion, either on this total field or XYZ component data. We've done some multispectral camera surveys as well, but not that much. In the future, we'll be aiming for doing radiometric surveys and electromagnetic surveys as well. So, few words about our magnetic survey system. It's a combination of a 3-component flux-gate magnetometer, fixed-wing drone, and equivalent layer modeling. The magnetometer is combined with our own data logger and uses rather high 150 to 100 hertz sampling, and by doing decimation and stacking, we reduce the amount of data and improve the raw data quality. So the sampling frequency is something to 50 to 10 hertz, and if we now consider that the drone is flying at the speed of about 20 meters per second, this gives us a spatial sampling of about 0.5 meter to 2 meter, which I think is quite sufficient for most magnetic work. The fixed-wing drone was selected because it utilizes aerodynamics. So with the same power from the batteries, we get longer flights, and because fixed-wing drone flies faster, it covers more mileage, and thus it becomes more cost-effective, so to say. And also, fixed-wing drones usually have just one electric engine, so there's only one noise source, which comes into account. And also, when we apply this flux-gate magnetometer, it's so lightweight that we can put and install it rigidly in a fixed position into the drone, and we can do this calibration of the sensor by rotating the whole drone around the flux-gate sensor. The key point also improving our data quality is this equivalent layer modeling, and which essentially handles for leveling the datasets, because flux-gate sensors, they seldom are absolute magnetometers. So we have to different magnetometers or flux gates to give different values of the magnetic field, so we do the tie line leveling and trend removal, which actually means mostly that we take into account the temperature change effects on the flux gate sensor. And of course, additionally, the heading correction is also inverted in this numerical inversion of equivalent layer modeling. But the best part of using ELM is this, that we can use the model once we've found good fit and found all the errors in view process. We can use the model to compute gridded data on an even grid at constant height. And we can also compute the derivatives. So it gives us lots of different benefits, this ELM. So coming back to what kind of experiences from fixed wing drones we have received. So this is what we started with, Terrain Scout, or most people know it by the name Skywalker X8. As you can see, there is a Pixhawk autopilot in there. And because we were a poor company in the beginning, we used a freeware mission planner software and still use that software for our flight surveillance. The drone itself, it was cheap and lightweight. There was plenty of room in the cabin there to put all the instruments. It was modifiable. For example, we installed a camera inside the box, and even there you can see at the back there is a parachute for safer landings. But this was not used for very long because it had problems. Also, the flight performance was poor. It was sensitive to wind. Flight paths were wiggling, and so there were motion noise. And also the flux gate sensor in the nose there was too close to the engine, so there was electric noise. Moreover, the flight times were quite short, say 35 minutes. So we wanted to look for something else. And we turned it to a guy, Olli Bori, who designed us self-made drone, shown here in the figure. The engine is now in the front, and the flux gate sensor is at the very end of the tail. And the key point here was that we tried to apply as non-magnetic materials as possible to reduce the noise the drone itself gives to the flux gate sensor. But the problem with this drone was that the cabin or this hull of this drone was pretty crowded. There were not enough space for many batteries, so flight endurance of flight times were only up until something like 1 hour, so it's not good enough. And also it was very tricky to work with all the equipment inside the fuselage. So our own pilot, Timo Åhman, then built us a next version Albatros V-tailed version, which was really used up until last year. And it had a much larger fuselage, and it allowed, for example, apply this multispectral camera inside there. And most importantly, the flight times now increased up to 2.5 hours. So it was very effective. But also Albatros met its fate. Although we used it almost like 40,000 line kilometers, it had problem that during belly landings, it tended to get damage, hit into the ground. Also, water and dust get into the cabin and then spoil our equipment. So the overall efficiency of this drone type was come to its end. And then we thought that why not buy ourselves a new drone. because recently there's plenty of different kind of drones up there. So we started to use this Foxtech, Chinese company Foxtech Loom vertical takeoff and landing drones from the beginning of this year. So not much, not very long we have used, but still we found them very useful. Again, the endurance of time, flight times reduced 1.5 hours, something like that. But because we have experienced less amount of repairs during landing, so the overall efficiency has increased. And again, you can see the magnetometer. It's located at the tail boom of this drone, and it's something like 1.5 meter away from the engine in the nose. So it's working very nice for us. So experiences so far, taking into consideration of this flight time of 1.5 hours, it's the practical effective length of the flight lines, taking away the turns and transit flights, is something like 70 line kilometers. Noise levels are, I would say, we have not made any like a true analysis on this, but I estimate it to be 5 nanoteslas, which seems high, but it's in our opinion good enough for most surveys. And still we use this fault difference as a measure, and 0.2 is nowadays our limit that we expect data to have when we do calibration or testing before doing actual surveys. And you usually have a field crew of 2 persons that operate 2 drones, and because the change time, so that means downloading the data from the logger, putting new flight plan and changing the batteries, it's pretty fast. So by using 2 drones, they both can be up on the air for more than 50% of the time. So that's very nice. So good conditions here in Finland during summertime. There's a long sunlight all day long, so 1,000 line kilometers is quite possible. But one necessity for doing these fixed wing surveys is beyond a visual line of sight mode. And luckily here in Finland, we have been able to enjoy that for many years now. We do apply it from Traficom, and there's 2 kind of permits. A quick one can be obtained within a week, but an extended one, say, takes about 1 month, because it has to go through this European flight agency. And to do magnetic surveys, we also need to have a photo permit from the Finnish arm. And quite recently, this autumn, we received operational authorization to work in BVLOS mode also in Sweden and Norway. And actually, we are about to start a survey in Sweden next week. So just to give an example, this is an area from North Finland of about 72 square kilometers, with a total of over 1,600 line kilometers. There was a crew of 2 persons there with these new drones. 36 flights were made in 3 days, so very fast operation. And here in this picture, you will see the polygon, and it's filled with our data, and outside there is GTK, Geological Survey of Finland, who has made this whole Finland covering survey, but it's measured using 200-meter line spacing, whereas our data is using 50-meter line spacing, and also our lines are slanted to better go through the geological strike. So now, if I were to swap between the GTK data and our data, you can clearly see the improvement, mostly because of the denser line separation. But to analyze or show you the quality of the data, this horizontal gradient image shows more clearly that there is a drastic improvement in the data quality, because if the GTK data is used as a basis for this horizontal gradient, it's almost impossible to see the continuity of some features in the data. And more importantly, these derivative operations, which are computed using this equivalent layer model, they can be used to analyze our processing, because if the data or the processing is made wrong, there appears artifacts, stripes, and hatch patterns here in the derivative operations. So we use these and utilize these to as a basis to redo our processing if something peculiar happens in these derivative maps. So what's next? We are very interested or very happy with this VTOL drone capacities, and we have already purchased a new one, a little bit bigger one. We call it Goose, and the aim is to increase the flight time twofold, so it'll be making 2 times longer flights. And also it's a little bit bigger, so we hope to install this total intensity measuring gamma detector inside this. It's not a spectrometer, but it's a gamma detector inside this same drone, or possibly with or without this flux gate magnetometer system. And we are also developing and building our own frequency domain EM system, which uses, at the moment it uses this ground loop as a EM source. And as this figure here shows, there is this even larger Mother Goose drone carrying it. But our experiences from a few cases using this VTOL drone to carry the receiver are a little shaky. So we hope to possibly build the receiver onto the fixed wing drone itself. So it'll make much safer operations that way. So to conclude with, we have successfully combined flux gate magnetometer with a fixed wing drone, and by using equivalent layer modeling to do the data processing, we get very good results. And compared to magnetometers, towed magnetometers that measure the total intensity, the noise coming from flux gate is bigger, but it's acceptable for most cases. BV loss is a necessity, and our experience from VTOL drones are very promising, and we're definitely going to use them a lot. So thank you for your attention, and I'm open for questions if you have any. So thank you.
Excellent talk. That was very, very interesting. I see one question here in question and answer, which I'll read out. Does your BV loss authorization have restrictions on the minimum distance between the operator and the air vehicle? Or else, what is the range you can achieve with current equipment?
Well, I didn't go into the details of the instrumentation, but in Finland, there is a very nice coverage of GSM reception. And if possible, we use GSM 4G, 3G connection directly. So it's not a radio telemetry at all. And there's actually no limit when using this 4G connection. So tens of kilometers, that's it.
Yeah, very interesting and applicable to doing large surveys. Awesome. I think we have time for one more question here, and I'm going to ask Mel's, which is, thanks, very interesting. What height do you fly at, and how do you terrain follow?
The height, flight height, depends on the tallness of the trees. So in North Finland, something like 30 meters from ground is achievable, whereas in southern Finland, trees are taller. It's up to almost 40 meters is the nominal flight altitude. And we always use digital elevation model, what we here in Finland can get from National Land Survey, and we build flight system so that it follows the terrain using the wave-one separation of something like 250 meters usually.
Great, thank you very much. I see there's a couple other questions there, but we're going to have to move on. So maybe if you would like to type out some answers to those in the chat, that would be good, or we can follow up with them later on in the discussion.
Yeah, I can do that. Great.
Great, thank you, Markku. That was a very interesting talk. I'd like to introduce our next speaker, presenting about suitability study of the semi-airborne electromagnetic method based on a multicopter system. Philipp Oliver Kotowski.
So hello all. I hope you can hear me clearly, and I hope that everything went okay with the sharing.
Looks good.
So can you see it full screen?
Yes.
Yeah, super. Very nice. So yes, as introduced, I'm Philipp from the University in Münster from the Applied Geophysics group. Yes, and we are working on an EM system. So this talk will be about the suitability study of this semi-airborne EM technique based on this multicopter system. So yes, to give you an outline, so I will give you some motivation about why we are doing this, and then introduce this method, and also show you the aircraft system we are utilizing. And the major part is showing you the survey results from Münster, focusing on the processing and inversion results. And in the end, I will give you a short summary so that you know what is happening here. Okay, so generally, what is the objective of this study in general? So the plan is to be able to demonstrate that multicopters are really suitable for semi-airborne EM application. And for this purpose, we have chosen this our survey area located in Münster, in this Münsterland sedimentary basin, which is yields very flat-lying, non-complex strata, and is easy to access. So it's perfectly suited to operate within UAS. Another plan is also to specify capabilities of the method and also restrictions. So I guess, as you all know, so why we want to apply this technique. So this technique is nice because it's low invasive, and yes, we are able to uncover conductivity structures in the subsurface, also down to 1 kilometer or even beyond that. This can be very useful for the identification of geological structures, as well as for groundwater level mapping or mineral exploration. And this is possible because we are unifying these ground-situated powerful transmitters and have only receivers on our airborne platform, so that we are able to really, generate a lot of power by our transmitter. Yes, and this can be also useful because we have a complementary technique to other known techniques. So we have heard already a lot about magnetics and about photogrammetry and GPR and so forth. So this is to enhance the picture we can get from the geological perspective. Okay, just to introduce the method. So there was a talk on Tuesday from Matthias Ronschka already, applying the same technique. So just briefly here, what we are doing is we deploy this horizontal electric dipole. I hope you can see my mouse as well. And injecting a current. This current will excite a primary magnetic field, and this primary field will induce currents in the conductive media, and this will lead or give rise to scattered fields, and we can measure the superposition of the primary and the scattered field by flying through our survey area, and yes, measure the field output. So as here in this example, you see the square wave input, and we fly through the area and measure the field in terms of components here, north, east, and downward component. And the idea of this method is to be able to estimate these magnetic transfer functions in the frequency domain, which give a relationship between the induced current and the observed B field. And yes, this is done in the frequency domain, so we have to perform somehow a Fourier transform and then solve this least square problem here by performing a regression for a range of frequency binge and for particular centered locations. Okay, so the aircraft system we use is a concept from MGT, which is composed of an Arialis octocopter. Here we have a data logger mounted rigidly directly beneath this octocopter. This is a Metronics ADU 08. And then we have this 2-meter long rod here beneath the logger with 3 sensors. So an IMU from Xsense, we have a flux gate sensor from Bartington, and we have a high frequency induction coil triple at the end. So this is our setup here. It's coming to the survey itself. So you see here Germany and close to Münster, close to the Netherlands. We have a covered an area of approximately 10 square kilometers. So in this area, we have installed 4 horizontally dipoles as transmitters. You can see them in these colors, here, green, blue, red, and magenta, and associated flight areas for each transmitter. So every transmitter was running separately, and they were not operated simultaneously. On the right side, we see the time series, so a segment of the time series for each transmitter. So we were able to achieve up to 20 amperes current amperage, and we have injected this 32 Hertz base frequency for in these transmitters. Yes. In black, you can see the flight lines. It was 150 meter spacing, and our sampling frequency for recording was 30 kilohertz. Okay, so first I will focus on analyzing the data quality in dependency on the distance to the transmitter. And here for this example, I have chosen transmitter number 2, what you can see on this map here left. And we see 2 flight lines and 2 distinct points on these flight lines, which differ in distance. So point number 1 has a 300 meter perpendicular distance to the dipole transmitter, and point number 2, 1 kilometer more in distance. And now we can have a look on the spectra we get at these points. So we can look on the spectral content. On the bottom panel, you see the amplitude spectrum from the transmitter itself. We can identify this injection frequency as well as odd harmonics going up to higher frequencies. What else we see? We see this weird shaped peak here at 8 kilohertz. And as you remember from Matthias, this is due to the pulse width modulation of the transmitter itself and not some kind of weird FFT artifact or something like that. Yes, if we look to the spectra estimated from in-flight data, so this is the downward component, and we are looking on induction coil data here. For point number 1, the closer point, we are able to identify all of these harmonics as well. We see that overall the noise power is larger for the low frequency, so below 100 Hertz, we have a lot of noise going on, as well as some other different features here. If we go to point number 2, the other point, we can see that these noise plateaus become more prominent here. So one is located from 500 Hertz to 1 kilohertz and from 3 to 6 kilohertz. We can have a zoom in for this first prominent noise plateau here on the right panels. And now it becomes clear that for particular frequencies, we are no longer able to obtain any signal. So this signal completely vanishes below our ambient noise level. So what are the reasons for this EM noise plateaus and interactions? So for this low frequency range, it is due to motion noise, because we are applying here induction coils, and if they are vibrating and we performing maneuvers, then we induce a lot of noise. But typically this is less than 20, less than 40 Hertz. Vibrations can be a little more higher in frequency range, and this medium to very high frequency ranges is just simply due to interferences coming from the UAV itself. So this can be maybe improved by just change the suspension of the sensors. But nevertheless, this vibrations stuff will maintain because we perform airborne measurements. Okay, in the next step, we can have a look on the transfer functions. So here I will show you one profile line crossing all of the transmitters. You can see it here in the red dotted line across the whole survey area. And we can plot this transfer function estimates. So these estimates are complex valued numbers. And here they are represented in terms of amplitude, the top panel, and phase, the bottom panel. And then we see for each transmitter this resulting transfer functions for the north component and for 3 different frequencies, and low one, medium one, and a high one. And the color just means that the transmitter 1 in green was running, transmitter 2 in blue was running, and so forth. And we get a very good coverage in this central area of our survey area, where we have data from 3 different transmitters. What we can see here is that we get very good data coverage up to 2 kilometer distance from the transmitter. So beyond that, it's become very noisy, and the data is very jumpy then. But we are able to get the good data quality in all kinds of frequencies. So from low to very high frequencies. We can use this transfer functions as an input for inversion. And here we have performed 2D inversion using Mario 2D code. So the initial model was a 50 ohm meters homogeneous half space. Yes, we included 2 components and 15 frequencies for the inversion. And you see the inversion output here in the bottom panel, reaching to 500 meters depth. And what we see is this major feature is this conductivity transition, which is slightly south dipping and in a depth region between 100 and 250 meters. So this near surface layer has a conductivity of approximately 200 ohm meters, and this bottom conductor of 20 to 15 ohm meters. Yes, so beside the transmitter positions here, you can also see MT and DC. So this means we have a magnetotelluric side here positioned, and direct current sounding performed near transmitter 4. And we can use this data or this information to validate our 2D inversion. So this is done here. So on the left figure now, we see in blue Occam and block model inversion result 1D from the direct current sounding. And we see in red here the empty 1D inversion result. And in black, we see a section or a crop section of our semi-airborne EM inversion result extracted beneath this MT side. So what is now striking is that that we achieve here very high consistency of all 3 models. So this DC and MT inversion results yield or reveal the same decrease, identical decrease in resistivity at this depth areas between 100 and 250 meters. So these are very fascinating, good quality data. Yes, and it's nice that we can validate it so nicely using the other methods, these independent methods. Okay, so coming to an end, I will sum everything up. So we were able to perform a pretty large scale, maybe for UAV conditions, complete survey, complete EM survey very efficiently with low cost and high spatial resolution based on this multicopter system. We find out that we have two major influences. So one is this octocopter related EM noise, and as well these motion noise effects below 100 Hertz. Yes, we get good quality, good data quality up to 2 kilometer distance from one of those bipole transmitters. And it was possible to identify geological conductivity contrast, which fits very nicely the geology we will expect on this site, and could be also validated independently. So in the end, it can be stated that yes, in fact, multicopters are suitable for semi-airborne EM applications, and they can be used as a nexus between conventional ground geophysics and typical manned airborne surveys. Yes, so thank you very much for your attention. That was all from my side, and yes, I'm open for questions here.
Thank you very much. That was an excellent presentation. I think I see Johannes has opened his camera there and would like to ask a question. So please go ahead, Johannes.
No, I don't have a question, but no, I have no question. This was by accident. I opened it by accident because I have the next talk.
Ah, my mistake. See if there's any questions filtering in, and there are some now. So the first question from Paul is, how long did it take to survey 10 square kilometers?
It was 4 days. So the flight time we have 21 flight patches, so individual flights of 30 minutes approximately, and within the survey took 4 days, and we was 5 to 7 people.
Very good. I had a question just about maybe the powering of these systems, because a lot of the magnetometers we use, the conventional method has either one has been to power it from the UAV's batteries, or two to have sort of an external power source, but then of course you're increasing the weight of your system. Are there any concerns that you've had with that, or how do you go about solving that problem?
In terms of weight conditions?
Yeah, just kind of the weight conditions, and then also powering these systems. Do they take a lot more power than, say, a magnetometer would, or not?
Yes, so this is really a problem. So it becomes very problematic if you want to survey for longer than this 20 or 30 minutes. And so, I mean, we overcome this problem by using these high power lithium batteries. But yes, so I can imagine it's still possible to somehow get even high and more high, as the higher energy batteries, but they are super heavy. So somehow we have to find this balance between weight also of batteries and energy level. So yes, it is a monstrous. This UAV also is a very great one compared to the smaller ones if you use them for magnetics. Yes, but these induction coils are very heavy. This is a problem if you want to use them. I mean, if you want to use flux gate sensor, this is fine, but yes, especially if you want to use high quality, high accuracy induction coils, you need this weight.
Yeah, so that'll definitely be an interesting challenge to move forward with. We have a question from Paul Mutton, and it says, is there any point in lowering the TX frequency with the lower frequency noise levels?
I mean, we can. The idea is why we use low TX frequencies is because we want to achieve this penetration depth, which are which are deeper seated to reach this deeper seated targets, and so this is the reason why we apply this lower frequencies for surveying. I mean, otherwise we wouldn't be able to get to this penetration depth. And yes, if someone is interested into more near surface features, then it would be better maybe to change the frequency, because you can get more energy on the higher frequencies then, and maybe overcome the ambient noise or the UAV related noise in these bands.
Excellent. Thank you very much. I will definitely have some discussions for you later on in the live session later, so I'll look forward to that. But I think we'll have to move on now. I think there's one extra question there that maybe you could type an answer out for, and then we'll move on to our next presenter. So thank you very much.
Thank you very much. See you.
Yes, thank you, Philip. Our next presentation is titled "Some Thoughts About Future Airborne EM Concepts and Novel Visualization Techniques." And I'd like to introduce our next speaker, Johannes Stoll.
Good afternoon, everyone. Katja, can you show the slides? Yeah. Okay. This presentation is a result of a collaboration between MGT in Germany and Creative Technologies based in the Netherlands. Creative Technologies is a software development company that offers innovative cloud solutions and mixed reality experiences to optimize operational workflows remotely. My colleague Katja and I will share this presentation together. Slide 2. We want to give you an example of how this collaboration can work using virtual reality. For this purpose, we show you data from a test project applying the semi-airborne EM method near a salt dome in North Germany. And Katja will present the results in virtual reality later on. First, I would like to show you where drone geophysics currently stands in achieving this goal of automation. Then I would like to introduce the concept of the semi-airborne EM process. And finally, Katja will introduce you to the concept of virtual reality and give examples. In this slide, the Drone Summit clearly demonstrates the huge interest worldwide to use drones, either in commercial projects or research. The interest in learning from others in order to progress faster has increased dramatically. It began as pilot programs and outsourced contracting. In the past decade, clients requiring geophysical drone services contracted drone geophysicists to conduct airborne surveys. This is changing now. Drones became more reliable and cheaper, making it affordable for almost everyone to acquire a drone and start playing with geophysical sensors and gaining experiences to integrate it on a drone. However, this is obviously a long learning process that requires a lot of geophysical know-how. New know-how needs to be acquired, for example, on navigation problems, on electromagnetic noise sources generated by drones, and also to understand the sensor models better. The commercial drone industry now is on the cusp of a new era of automation. The next step will be to scale up airborne operations for the sake to achieve better utilization, further reduce costs, perform larger projects, and gain higher profits. It involves to share data and results with colleagues and clients regardless of the location. In the following slides, this will be demonstrated through a semi-airborne EM project on a field in northern Germany. Next slide. As Philipp Kotowski from University of Münster already explained, The semi-airborne methods uses an electric dipole on the ground to generate electromagnetic signals in the range between 10 Hertz to some tens of kilohertz. The power source is a 10 to 60 kilowatt generator capable of producing bipolar current signals, square waves, and electric currents between 10 to 30 amps. The primary signal generates secondary currents in the subsurface. 3 orthogonal induction coils carried by a drone, multicopter, or helicopter are used as receivers. The time series of the components are recorded there. Sample rate is 260 kilohertz. The measurements take place in the frequency domain. Or this method is a frequency domain methodology. With a specially developed data processing, frequency spectra of the components are determined over 1 to 4 second time intervals. Then the transfer function is determined for certain evaluation frequencies between the fundamental frequency and the harmonic frequencies up to 10 to 20 kilohertz. Next slide. The semi-airborne EM method is a frequency domain method. The fundamental frequency is between 1 and 100 Hertz. Due to the large slope of the square pulses, we generate many harmonics up to some tens of kilohertz. For a horizontal electric dipole, the in-phase and out-of-phase component can be plotted as a function of frequency or induction parameter. For small induction parameters, one is in the so-called resistive limit, which is a near field limit, and for large induction numbers, parameters, one is in the inductive limit or in the far field limit, where the out-of-phase component is larger than the value of the in-phase component or primary field. During the flights of the drone, we reach the near field range close to the transmitter cable and the far field range in about 500 to 1000 meters apart from the transmitter cable. The measurements therefore constantly move from one range to the other during the flight. A similar cause result is in the elevation is shown on the right. The curve can be converted into a conductivity model by numerical modeling. Next slide. Below, we show the semi-airborne EM measurements near a salt dome in northern Germany. The flight lines are shown on the top right. They extend over 1 square kilometer. The line spacing is 50 meters. There's a salt dome called Bramel, which is located about 2 kilometers north of the flight area. The survey area is geologically located in an area that was part of a large-scale intracontinental sedimentary basin in the Permian. Tectonic expansion movements of the Earth's crust initiated the rise of salt. We have digitized the different geological layers. The geology is shown together with the results of the modeling of Katja's semi-airborne EM measurements in virtual reality. By means of a link, this result can then also be shared with clients or all participants. And now Katja will take over.
Okay, now I'm unmuted. Thanks, Johannes. Yeah, let me continue. As Johannes said, I'm working for a company that is working on solutions to visualize geological data or geoscience data in the virtual room, or also in the mixed and augmented reality. And I will tell you later what that exactly means. And we decided to test that also on this data. My background is actually that I have been working in the oil and gas industry, and that's also mostly, and that's also why some of the slides show more oil and gas related pictures. But that it's the same, it's geology that we are looking at, it's a subsurface that we are observing. The standard approach, if you have a 3D model, is that you have that you show sections and depth slices. Maybe you show that on paper or PC screen. You use 3D subsurface modeling packages on your PC, so you always see and you share your figures in video conferences, for instance. But you always see everything in 2D in the end. You maybe see it a little bit 3D when you start moving the model. The new virtual and extended reality approach instead allows you to see 3D holograms in your room, or pseudo holograms in your room, in your own room. It's cloud-based, which means you can get to the data from anywhere where you have a proper internet. So, and you can host virtual meetings, and that's what I will show you later on. To clarify some of the terms, mixed virtual and augmented reality. Mixed reality means you have some smart glasses where you can look through, so you see your reality, and at the same time you display digital content, so you display holograms or other information. Virtual reality, you maybe know from gaming, that's a closed device, so you only see a virtual room, and in this virtual room where you're fully immersed, you can display any 3D objects, which, like in our case, geological models or pictures or whatever. In both cases, mixed and virtual reality, you have your hands free and you're fully immersed and can interact with the objects. Augmented reality now would be typically done on you would typically see that on a phone, a smartphone or a tablet. And maybe you have heard or played the game Pokemon Go long years ago. That was maybe the first or one of the first games using augmented reality. That is when you see through the camera of your tablet or phone, and at the same time see some artificial objects, and you can walk around them. So they give you a full 3D impression. So how would we get Johannes' model or the Donner model into the virtual space? So we start with a computer and a standard software application, and then we send it through an add-in which is available at this moment for certain software packages, and you can send it to the cloud. And from the cloud, you can get the data on your device with a certain tool called baselines in our case, and you can host 3D meetings and and discuss the data. So you can meet with real people. So it can be 2 real people and 2 people who maybe sit in here. It's an example in Germany or Ecuador. They can all meet and speak and interact with the model like you would do on a screen too. But now you have it really 3D. You can walk around. I will show that. The problem with showing really virtual reality or mixed reality or holograms is that, again, we are now in a video conference, so everybody is seeing everything on screen. Therefore, I decided that it may help if I take some videos, and that's what I want to show you now. Here you see me in the Vladingen office. It is now in the Vladingen office in the Netherlands. That's the model from Johannes. You see the salt dome and the horizons, and that's the add-in here. And I send a picture there already, and now I will send this data here. And now I can go and visualize this data on the HoloLens. So that, if you remember, that's mixed reality. Here you see me now in a room, and in this room, that's the model from Johannes. That's a resistivity model. In the end, it's displayed similar to how you are maybe used to displaying seismic, at least in oil and gas. That's how you display 3D seismic. So Johannes calculated from his measurements, he calculated the model, and what you see, the calculation points are these dots that you see here, and the model is really that's different slices and sections from the model that are moving here. And also what you saw, if you took notice, that was my colleague, because it's a third-party visualization here at the moment. He's taking this video, looking at his phone, seeing me, that's again from my perspective, that's in the HoloLens. Here you saw my colleague who's taking this video. Yeah, and he sees the same. I move the seismic, or not the seismic, the electromagnetic model, and he sees it moving. So that means you can display it everywhere. I should also say maybe that the top part is the flight routes, but you probably already have guessed that. And if you want to know the results here, the low resistivity is in bluish colors, and red and high resistivity is in red colors. So you see that in this area we have the finding was that there was a low resistivity line here, so which may be salt water. Yeah, so good. So that was me working with the model alone, and I hope you could see stop this, how this my colleague was really filming me, because there was sometimes you saw the perspective of me. That was when you saw the model and you saw the person with the camera, or not with the camera, with the smartphone, and in other occasions you just saw me working with the model. So when you did not see me, then it was my view, and when you saw him, you saw me, then it was his view. And now I want to show you how that would look like from third person perspective again when you work in collaboration. Here you see the avatar of Johannes, so it looks like him, I hope. And we both see the model, we both can work on it, we both can evaluate, does it make sense, does it not make sense? I mean, I have to say this is a very simple model because it's a flat or layered model, so it's almost the same. It's almost a 1D model, really, I have to say, but that's just the results from the measurements, and that also from the modeling of the measurements, and that actually also makes sense for that area. You can also collaborate with more people. You can collaborate here. That's a collaboration of people, 3 people who are in different areas. They can be just anywhere. Use United States, Texas, I don't know. Let them be anywhere, and collaboration. And you see, you can also display 2D planes. You could display figures like you would in a PowerPoint, and all these people can interact here with the model and yeah, and discuss the results. As a last, I would like to show that you actually really anywhere can work with this data. So last week when I visited the Netherlands, we decided to also take a video of the dark data from Johannes just out in the field or in a park close by, and film the situation. So you see we are outside. We can also outside, just with a normal internet connection from your phone, you can really interact with the data together and work on it. So that may be also a vision for the future, that you could directly take your data when you're in the field, do the measurements, may send them to some cloud and do the conversion and so on, and then visualize them on any device in your field. Good, let me summarize our talk. We see a major trend towards automation in drone geophysics. Also in semi-airborne electromagnetics shows, and I guess that will be similar in other applications, that there's a trend to aeric geophysics, so that you will really have 3D models, and therefore you have a need to display 3D model. There's a lot of data involved, so you want to display that. We think that high-end 3D visualization in extended reality, that's mixed reality to augmented reality to virtual reality, is now available and applicable to large geophysical data sets. And 3D extended collaboration tools allow and facilitate sharing 3D models and study results, and allow for global meetings around 3D geoscience models. I would like to thank also my colleagues in the Netherlands who helped me taking this video, because you see there's a lot of actors involved and somebody has to film it. And I especially want to name Markku, who helped me a lot here. And also I want to thank you for your attention.
Excellent. I think all I can say after this is wow. I have a little bit of experience working on something like this back on my capstone project when I was in engineering, and let me tell you, this has come leaps and bounds further than what we were able to achieve in a semester. So I am just blown away with this kind of technology and what you guys can show with that. I'll jump right into the Q&A here. We have a question from Alex, and it says, in your experience, what do you find the client benefits the most from virtual reality, AR, MR, and visualizations over regular computer displays?
I think the highlight is really that you can immerse the data, you can see it from a really different perspective. I mean, if you look at the seismic data, you can really blow it up and see it very large. I mean, here we don't have seismic data, but and you can really collaborate around these models. You get a totally different insight when you can actually look at that. Also, when you have customers also which are not so familiar with geological display, then it's for them on for with 3D display. Geologists are usually good at that, but other people are maybe not so good. It's much easier for them to really understand the geology or the model because they can just walk around, and it's different. It's like looking in 3D. It's not like in a figure you always have to think the third dimension.
Thank you very much. Nathan, did you have a question? Saw your hand up there for a sec.
No, that was an accidental hand raise.
No worries. I will look at our next question here from Mel. It says, what limitations are there on the amount of data that can be visualized? Example, I imagine visualizing a full LiDAR point cloud would be beyond the scope of the application.
I'm not exactly sure how large that would be because I come from the other direction, so then Johannes may know how large that data set would be. What I can say that we have displayed seismic up to 1 gigabyte, but at that point it gets a little bit shaky, I have to say. So we can display it, but it's not as fluent as you have seen it here in this model that we are displaying. So that works. And we are working on improving that in the company, of course, so that you can work more with a certain level of detail, so that you only see the data that you really can see, so that you don't load all the data at once. So we are not streaming the pictures at the moment. It's really we have the data on the device, and then they will be rendered, so displayed on the device, and therefore we are improving the techniques to use less. I mean, to work with large data sets by only downloading the amount of data that we really need to display.
Excellent. Yeah, I know off the top of my head just like hundreds of applications that you could use this for. Like I've collected digital outcrop models that would be perfect for this if you're trying to visualize them in, you know, a lab setting. So I think there's, yeah, LiDAR is another great example. There's so many applications of what we could use this technology for. And moving on to that point, we have a question from Kanita that says, can you integrate geologic models as well as geophysics?
I mean, geological models, geophysics, I mean, the question is, what do you want to display? I mean, anything which is 3D, you can display in the end. At the moment, we display like here, that's voxel grids or like seismic lines. Yeah, so we can display points, and we can display horizons. We can display faults. That's just surfaces. So we can display any surface. And we are starting to display grids. So it depends what type of geophysics data. I mean, here it's a depth scale, but in theory, you could also use another scale, yeah, like apparent depth. So it's anything which has 3 x, y, z of any kind you could display. May need some additional work depending on the data, so data type. And of course, we cannot send data from every application. We now have 2 software packages that we can directly send the data, and if there's need for others, then new add-ins would be needed to really send the data to the cloud. But in theory, I would say it's doable.
May I add that we included geology in our data. You can see it here on the last slide, you see the results, the geophysical model, conductivity model, immersed into the geological model.
Yeah, I mean that's maybe I missed saying that. I was speaking so much, but I missed saying that. So that's really the geological model. That was a digitized model, and here you have the small resistivity model. It's different scales, right? So
excellent, thank you. And then I think we have one more question here, which I'll answer live, and it says maybe a couple more, we'll see. Thank you, very interesting presentation. How do you determine the best interpolation method for building your 3D models?
I mean, here the 3D model. I mean, you mean the drone model here, not the drone model, the resistivity model. And here, this is actually inversion. No, it's forward modeling data that was provided to me by Johannes. Yeah, and here it's just I would say it depends on the data, and also I have not done the interpolation in this visualization software package, but I have done that in another package. And in this case, it made most sense to work with something like nearest neighbors, but that wouldn't be the normal decision. It depends a little bit on the data set, I would say. I mean, here everything is just straight. And it's not a part of the visualization in the end. It's more the work you do before.
Great,
I mean,
thank you.
You can work with the data in here you can add notifications, nodes and stuff like that, and do a little bit. There's concept modeling, but the real calculations or the real math is still done on the computer. So this is not going to replace computers in the next future. So we will still work on computers and work with 3D packages, but it will add on to really showing the data, demonstrating the data, and understanding the results.
Yeah, I agree. I think there's definitely a huge potential for this type of technology moving forward. So it's really amazing. I think we have time for one more question here before our break, and that is, what is the behavior for high resolution data? So probably to the point, again, if you have a lot of data, is it clunky at all or anything like that? I think that might be where that question's going. And when you step closer, does it become clearer? Like zooming into a GIS program. So I guess, can you interact with the data and zoom in physically as you move around, or do you think that could be possible by any means?
Let me go from the last question. So I'm not exactly sure if I understand it correctly, but what you can do, you can enlarge your model here. I mean, we have to speak about two things. One is the 3D package on the screen. So that's nothing we have developed or which we have now work much, and there you can of course zoom in. But when you're in the system, you can walk into the data and get closer, and it gets bigger. So it's a real interaction. When you're very close, depending on the device, you may see it vanish a little bit. I mean, that's maybe for people who have worked with some augmented, who was asking that. About the amount of data, I tried to answer that before. That's also still limited, also with the point loss. I don't exactly have the number of points that we can display at the moment, but I could check that. But that's of course also still work in progress. I'm not sure if I really answered that question, but the best is really to try it. So if you're very excited, send me an email and I will let you know how you can try it on a test thing. And then at least you can, on your phone, I mean, so that would be easy. Also if you have Oculus or something. And the first question, can you remind me what was the first part of the question?
The first part of the question was just what's the behavior of the high resolution data? I think to that point, it was just, can you zoom into the data was more sort of the idea.
You can zoom in. You can zoom in to a certain extent. I mean, we display everything at the moment. We display everything, so you have the resolution that you send there. So we do not yet have this level of detail or just in the beginning. So that's what is going to be developed, that you really have this level of detail, that you start with coarse data when it's small, and when you zoom in, that you see more the details. So now you see really what is there.
Excellent.
Yeah.
Well, thank you very much. And to your point about the emails, if all of our speakers from this morning could post their email into the chat, that would definitely help. And it's also on the screen here, as you can see. But maybe post our previous presenters as well, post your emails in the chat so it can facilitate people reaching out to you guys. And with that, will conclude our morning here. We're going to have roughly about a 15-minute break, so we'll be back here at the half hour for the second half of our talks today, which will be looking at seismic. So stay tuned, and I will see everyone soon. Nathan, is there anything you want to add?
I was going to say thanks to Johannes and Katja. Great presentation. The virtual demonstration for Skyfront is not going to be happening, so we're going to start. We'll pick up with the keynote at 45 after the hour.
40.
All right. Hello again, everyone. Before we get going here, I just want to give a special thanks to our platinum level sponsors and our silver sponsors again. So for our platinum sponsors, we have the Axiom Group, Geometrics, Sequent, and Skyfront. And for our silver sponsors, we have Collier Geophysics, Edcon, PRJ, Medusa, and Southern Geosciences. So thank you once again for supporting this awesome week of drone geophysics.
All right, Callum, I think I'll just introduce our next speaker. If we're ready here. Presentation title is Airborne Sensing of Seismicity and Other Phenomena with UAS. And our next speaker is Jamie Jacob.
Great, thank you very much, Nathan. Appreciate it. Let me start my screen sharing here. As Nathan mentioned, the title is Airborne Sensing of Seismicity and Other Phenomena using UAS. And in this case, it's a pretty unique platform of UAS that we typically don't think of. You know, we're not utilizing a drone here, but it's actually a balloon, and I'll talk about why we're doing that in a minute. And also what I mean by other phenomena, because obviously the interest here is in earthquakes, but I'll talk about what we've done previously with airborne sensing, a similar type of phenomena, and how we're utilizing this for seismic measurements. This is a joint project between OSU, Sandia National Laboratories, and NASA JPL. And of course, I think the first question that comes up is, well, why is NASA JPL involved in this? And they're actually driving the project because they're interested in seismic measurements on Venus. So in this particular case, with Venus, there's very little that we know about the Venusian geology, but there is evidence that there is significant seismicity on the planet, and they need some way to actually measure this. So due to the really hostile environment on Venus itself, which has temperatures on the order of 500 degrees Celsius down on the surface, becomes really problematic in terms of putting sensors actually on the ground on the Venus surface itself. But if we go to the upper altitudes, we actually find that above the cloud layer, the atmosphere is actually fairly benign and almost very Earth-like in terms of temperature and pressure. So as opposed to around 90 atmospheres that we see down on the surface, we see about 1 atmosphere of pressure above the cloud layer, and essentially room temperature. Even though it's mostly CO2, becomes very benign. And in that case, we can look at then deploying other types of platforms. And NASA has been studying various airborne platforms, including drones, but this particular effort is focusing on the deployment of balloons that will deploy sensors hanging below those to be able to utilize those for the seismic measurements. Now, in this particular case, what we're utilizing are infrasonic sensors. So these hang beneath the balloon and will pick up the seismic waves that are produced by the earthquake as the ground shakes. Essentially, you get the epicentral infrasound coming directly from the quake, but as the seismic waves are propagating over the ground, you also get secondary infrasonic propagation. Essentially, the ground acting, much like a speaker, creating these low pressure waves below the level of human hearing that are then picked up directly by the infrasonic sensor. Now, the benefit of putting this on a balloon rather than something like a drone is the balloon moves with the wind, and since it's moving with the wind, you get no wind noise. So you have a very, very low background level in terms of that wind noise. Now, for those of you not familiar with infrasound, we're talking about frequencies that are below the level of human hearing. So these are below 20 hertz, and typically we're looking in the 1 to 10 hertz range in terms of being able to pick these up. And these are very common. Geophysical sources are predominant modes of infrasonic transport through the earth, and so these include both seismic sources, atmospheric sources, as well as ocean sources. And one of the benefits that you get with infrasonic propagation is, unlike high frequencies, which are very easily damped out through the atmosphere, and typically at a high frequency you're usually only talking about a couple of miles of propagation. With infrasonic sources, these will travel for very, very long distances through the atmosphere. And essentially you have the atmosphere acting like a waveguide, which helps contain this propagation and is able to move these infrasonic signals for very long distances across the Earth. And Sandia National Labs in particular has been utilizing this for various detection of things such as nuclear detonations across the world, but as well as things such as lightning and even meteor impact. So as meteors are entering the Earth's atmosphere, interacting with the atmosphere, and emanating these infrasonic signals, you can actually then pick these up. Now, recently, the team at Sandia with JPL were able to demonstrate utilizing these sensors on board balloons to be able to pick up seismic measurements. And this is actually from Southern California quakes, demonstrating the capability to pick these up. So this has been demonstrated as a potential way for seismic measurements. However, this one case was fairly unique, and it was a target of opportunity that they were able to pick it up after the Northridge quake. Now, just very briefly, I'll provide some other ways that we're utilizing infrasound to be able to pick up natural phenomena, and in particular we've been focused on severe storms, and there's been great evidence that rotating phenomena such as supercells emanate low sound or low frequency noise in the infrasonic regime. And there's several theories related to that, primarily due to the oscillatory behavior of the vortex core, as it's essentially bouncing back and forth and then emanating these low frequency pressure waves. But that does provide a potential to be able to detect these as the tornado is forming, before the tornado is completely formed and it touches the ground. It also provides the benefit of being able to protect or be able to detect very low intensity tornadoes on the EF0 and EF1 scale, which typically become much more difficult to detect utilizing radars. So there has been deployment nearby the OSU ground infrasound array to be able to pick these up, and you can see a tornado from 2017 that was just south of here that our ground infrasound array was able to detect. And the type of signals that you get off of this, you can see the raw sound pressure level that the infrasonic microphones are picking up. detect a very large increase in the infrasonic propagation during the actual period of the tornado. And currently what we're focused on is utilizing arrays of multiple infrasonic sensors on the ground to be able to provide both bearing and range as these infrasonic sources are developed during severe storms. And it's not just tornadoes, but it is also other phenomena such as hail that is generated at high altitudes, and so there's a potential of being able to pick that up prior to the hail actually developing and then falling as dangerous precipitation. So what you'll notice, and I'll show a couple of the power frequencies from some of the other airborne measurements here later, just to give you a sense of scale with this. So you see an increase in both the frequency as well as the power level as this storm is actually forming within this particular regime. And so we'll see similar things in terms of the seismic measurements as well, but at much shorter time scales as we have these seismic waves propagating as part of that earthquake event. Now, what we're utilizing for this are what are known as high-altitude solar balloons. And this has been an effort that Sandia has been developing several years. Danny Bowman, who's leading this effort, presented this at AGU several years ago, primarily for atmospheric measurements, but then realized that, well, this will work really well for being able to carry some of these payloads aloft as well. And I'll go through a little bit in terms of construction, but these are some great advantages in terms of being able to utilize these. One of these being that they're relatively low cost, but it also gives us multiple ways that we can actually deploy these systems within the field. That includes a pure ground launch, as well as a what we call a grand slam launch, which is essentially using a weather balloon to take this aloft and then drop it down, augmenting this with helium on the ground, and then applying different methodologies during the actual launching of the system as well. Now, for the focus of this project, it was developing this as a Venus balloon analog. So I'll talk a little bit about the balloon, but then we'll come back and focus on the payload and the seismic measurements as well. One of the great advantages of this is these are really low cost. The materials are very low cost. We have our undergraduate students build these in the lab. And then since we don't have to use helium for this, for the ground launches, we don't have that expensive helium cost as well. So from an atmospheric measurement perspective, it's a really great tool, particularly for a university. Now, why Oklahoma? They've already demonstrated that they can do this in Southern California. Well, Oklahoma has a number of earthquakes due to the fracking boom. And so these are relatively consistent. So the goal here is for this year and next year, launch multiple balloons simultaneously to be able to capture these events from different locations. So predominantly what we're interested in is this cluster here between the Oklahoma City and Woodward region, moving kind of northwest, and we're predominantly located right around here in this particular region. So our goal is to be able to launch these during the time of year where we have mostly westerly winds that will move the payloads through these seismic clusters that we're getting. But you'll notice there are other events throughout the state as well, just not these really dense clusters that we see. So here's a quick demonstration of kind of a balloon assembly. We'll notice we're just using a polyethylene material here, so very lightweight film. This essentially serves as the restraint, which provides the solar envelope which the sun is heating. So where does the lift come from for these balloons? Well, it's just heating from the sun. So we launch them in the morning, and the sun will keep that gas heated, slightly elevated temperature to provide the buoyant lift throughout the entire day. So you can see the size of the balloon. To increase the heating, we actually use a charcoal powder on the inside, so that darkens the balloon material, and that darkening then allows the sun's intensity to be able to heat the atmospheric air on the inside, and that provides your buoyant lift. So here's a quick video of one of the early launches, time lapse, so you can see what this looks like. We do an inflation with the fan on the ground. You'll notice it's being blown around by the wind. Move it over. The sun starts to heat up the air on the inside, and notice it's not completely inflated. This will inflate more over time, and then the balloon takes off with the payload in hand. And you can see some of that charcoal powder falling out as it moves along as well. Now, predominantly we're focused on two launch mechanisms. One of those is a ground inflation, which you saw right there, where we're inflating it directly on the ground. And the other is what we call a grand slam, where if, for example, it's a cloudy day, we're not getting sufficient solar irradiance to be able to do that heating, then we'll use a weather balloon to launch it aloft. And then when the balloon bursts at altitude, it will actually inflate the balloon on its way down. I'll show a quick video of that as well. Now, to give you a sense of scale of the balloons, these are relatively large, but also lightweight. We're talking only, total a couple of pounds worth of balloon material here in terms of the weight that we have. Now I'll show you what these looks like from the ground, and you kind of get a start of the sense of scale of the lifting force. You can see our paracord here that are pulling the payload aloft, and so it's lifting it up off the ground. And very taut lines due to the tension being generated by the buoyant lift. And as we let go here, you'll see the balloon take off. Now this is still slightly inclined. We're still holding the payload onto the ground here, and so the wind is actually acting like a sail, pushing that the side of the balloon inward. As we release this and the balloon then starts to move with the wind, you no longer have that wind force actually pushing it on the balloon, and then the balloon starts to go through the process of a completely inflating. And you'll see the full inflation here and there. And that's what it looks like from the payload's perspective. Show a quick video here of our derailleur mechanism. Since we have two seismic payloads on board, separated by enough of a distance to give us granularity between the signals that are being measured. These signals are propagating at the speed of sound. So based upon the sampling frequency that we have on the seismometers on board, we want to be able to at least provide several samples that the signal is picking up, so that way we can provide the differentiation and determine where that signal is actually coming from. So you can see we have an automated derailleur system between those two payloads that as we launch the balloon, it separates those payloads by about 30 meters or 100 feet or so. So that way it gives us enough distance between those two different seismometers that we have on each one of those to be able to do that measurement. Now I'll skip through the Grand Slam test just due to the sake of time. I do want to mention that we do have to recover the payloads after the fact, so we're not sending the data back in real time. We're monitoring the telemetry so we can tell where the balloons are at during the actual flights. But once they land, we have trackers, and then we have to go out and actually recover them in the field. So this isn't. We do have some actual field geology in here where we have to go out and get dirty to be able to do the recovery of these. It gives you an example of what a typical launch looks like. Again, note, we have usually two balloons that are launched. This gives you an idea that even though the balloons may be tracking well with one another, we typically launch within anywhere from 15 minutes to an hour. Both the balloons, due to slight differences in elevation due to the inflation of the balloons, you can have really different flight trajectories with these. And so you'll notice here that they diverge. They stay together for a while and then they diverge, which is still okay because we want to have that difference between the two locations as we're picking up the signals. I'll come back to McAllister here in a second because that's going to be one of our sources of our test signals that we're currently utilizing to validate the methodology. So these are all of our launches from the 2021 campaign. So you can see them here launching mostly from Stillwater and then diverting across the state. typical sample track. You'll notice here the track of the balloons, the altitudes. These are typically going up to about 20 kilometers. And then we're also tracking the ground locations for the different seismic responses, so that way we can correlate those. The goal here is to be able to develop the proof of concept and to demonstrate that we can actually pick these signals up and then compare those with what we're getting on the ground signals. So this is what the typical signal looks like. We have the barometric pressure that we're picking up on the actual seismometers, and then we pass that through a filtering so we can put this into a power spectrum as a function of the frequency, and then we're looking for these spikes down here for the typical infrasonic measurements. Now I mentioned the McAllister tests. These are actually, we're utilizing the McAllister Army Depot in their daily blasts that they conduct as one of our test sources. So you can see here on this particular day, they had a number of different blasts that they conducted, each separated by about 20 seconds or so. And as the balloons are flying north of McAllister, this is about 60 miles north, that we're able to pick these blasts up as this is propagating through the air. And so then we're able to take that information, that signal that we're getting, and then propagate that through to be able to identify each one of these sources specifically. So next year we'll be focused on taking these again back out into the field. This year was primarily proof of concept. So the goal for the 2022 campaign is to be able to launch these balloons and get lots of really good seismic data, and hopefully we'll be able to present results of this next year. Thanks for your time. I'd be happy to take any questions if there are any.
Thank you. That was a very interesting talk on a unique platform, probably for most of us, and a unique sensor payload as well. So I invite people to ask any questions that they have into the chat quickly, and maybe if you could type your responses. I think we're probably going to have to move on for the sake of time here, unless there's any that quickly come in. But thank you very much. That was a very interesting keynote presentation.
No worries, and feel free to reach out if anyone has any questions.
Yeah, if you could actually type in the chat your email too, that would be great, and that goes for all presenters today. Thank you.
Will do. Thank you.
And also, we will have a discussion at the end of our talks today, if people want to stay on and discuss some pretty amazing technology. So without further ado, I'd like to introduce our next speaker. The presentation title is Drone-Based Active Source Multi-Channel Seismic Survey System. And our speaker is Takeshi Tsuji.
Thank you. Can you hear my voice?
Yes.
Okay. Wait a moment. Can you see my screen?
Yes.
Okay, thank you. My name is Takeshi Tsuji from Kyushu University, Japan. So today I talk about the drone-based, the active source multi-channel seismic survey system, as you can see in this movie. Wait a minute. Okay. So firstly, I talk about the purpose and objective of this project or study. So as I talked, we try to develop the active source multi-channel seismic system for the UAV. And as you can see in this picture, we deployed a small seismic source system at the leg of the UAV, and we deployed a multi-receiver system array on the UAV. And using the single UAV, we try to investigate the shallow geological structures from surface to 2 meters based on the surface wave analysis. And using the multi-UAV, we explore the deeper geological structure from surface to 100 meters based on the reflection and refraction analysis. And using this kind of device, the system, we try to conduct the seismic survey at a limited accessibility area such as volcanoes. And furthermore, we try to automate our seismic survey. And furthermore, we try to monitor the geological formation using this, the automated UAV system. So originally, we developed this kind of the small seismic, small active source seismic system for the space explorations, such as Moon and Mars. So as you know, the seismic experiment explorations is very important in space environment, because we would like to have explore the resource such as ice on the Moon or Mars. And furthermore, the geophysical exploration is important for the civil engineering, because it's related to the base camp constructions. And of course, it's also contribute to the science. So firstly, I introduce the active source multi-channel seismic survey system on the Mars and on the Moon and Mars, because it's almost same as the seismic system for the UAV. So in the space environment, the source and receivers are very limited. So here we assume that there is a lander and rovers on the Moon or Mars or space environment. And for the lander and rovers, we deploy the source and receiver. In this schematic image, the blue square is the source and red squares are receivers. So using this kind of a limited source and receiver, we try to conduct the 3 seismic survey using the limited seismic source and receiver system. And the first survey is the surface wave analysis. And using the rover, there's a small seismic array system on the rover. So using this small offset seismic array, that we estimate the S-wave velocity in shallow formations. And for the seismic refraction analysis, we generate the seismic source at the lander, and that seismic signal is received by the rover, so that we can estimate the S-wave velocity structures from surface to about the 100 meter using this kind of the refraction wave. And of course, we can observe the seismic reflection wave too, and we can image the subsurface structures. So this geometry is very similar to the UAV-based survey. Our UAV have our source and receivers. So the source seismic signal generate this UAV and receive another UAV. So we can conduct these 3 seismic surveys. So to evaluate the efficiency of such a limited and source and receiver system, we conduct the laboratory experiment. We prepare the sand layer in the laboratory and try to identify the suitable source parameters and receiver geometry using this test field. And here we use the very small molar as a seismic source. And we use the geophone element for the receivers. And we deploy the source and receiver on the laboratory, and the receiver, and we change the receiver geometry, especially that we change the offset of the receivers, and evaluate what kind of seismic data can be obtained. So this case is the very small, short seismic array, the 9 receiver with 0.1 meter interval, like this picture. There's a source here and 9 receiver, 9 geophone aligned within the 1 meter. And using this system, we can obtain this kind of shot togethers. A horizontal axis is travel time, and the vertical axis is distance from source to receiver, or offset. And here we can see clear surface wave. And from this surface wave, that we can calculate the dispersion curve, and we can obtain the S-wave velocity profile, the depth profile. It's a very shallow, from the surface to 50 centimeters, and horizontal axis is S-wave velocity. So at the one observation point, we conduct this kind of short seismic active source seismic survey. We can obtain the S-wave velocity profile. So if we apply this kind of seismic survey at the several points, so we obtain the three-dimensional S-wave velocity model like this. So in this case, the single UAV can carry this seismic array because it's a very short, just 1 meter. And furthermore, in the laboratory experiment, we measure the signal propagations using the longer receiver arrays, the 9 meter, the 9 receivers with 1 meter interval. So we obtained we acquired this kind of the shot together. The horizontal axis is travel time and the vertical axis is offset from 0 meter to 10 meters. So here we can observe the seismic refraction wave here. So from this refraction wave, that we can estimate the P-wave velocity of first layer and second layer like this. So if we record the source signal at longer offset, we can estimate the P-wave velocity. So if one drone carry the seismic source system and another drone or UAV carry the receivers, we obtain this kind of the data. So in the next step, that we try to conduct the field experiment using the very short, the 1 meter seismic array at the beach, outside in the beach field experiment. So I do not explain in the detail, but we acquired a very beautiful dispersion curve like this. And this is, oh, sorry, it's a bit erased anyway. So this is the S-wave velocity profile acquired in the very short array system. And the depth is from surface to the 1.5 meter. And horizontal axis is S-wave velocity. It's a very high, error is very small. So then we deploy the similar seismic array system on the UAV, and that we succeeded to obtain the very short seismic seismic record of short seismic array. So this is a picture. As I talked, our source system is located at the leg of the UAV, and the receivers is deployed here like this. And to use the UAV for this kind of the seismic survey, we needed to downsize the data acquisition system. Especially the data logger, the commercial data logger is very big, so that we downsize. We made the small size data logger. The weight is less than 1 kilometer, so we can carry the data logger here. And this is the geophone deployment. To reduce the noise from the UAV or this array, that we use the string to deploy the geophone, and we try to decouple the receiver from the UAV body. And after that, we deploy the UAV, the geophone array, that we generate the seismic signal using this kind of the very small motor. So that this source system continuously generate the chirp signal or sweep like this, and by stacking the chirp signals, that we improve the signal to noise ratios. So even if, although that we try to reduce the noise signal from the array using the string system, but honestly, the noise was included in the data. I don't know, there are many noise. So the noise is very dominant in the dispersion curve using a conventional surface wave analysis method. So we developed a new method based on the continuous wavelet transform. So using the drone, the seismic data, active source seismic data, recorded by the UAV system, that we can obtain the very stable dispersion curve, and we can estimate the S-wave velocity distribution, S-wave velocity profile at the measurement point. So, and then we acquire such a surface. We record such a surface wave. We conduct the surface wave at several points, and we can construct the three-dimensional S-wave velocity distributions of shallow formations. The depth is very short, the surface to just 1 meter, but we can obtain the three-dimensional S-wave velocity distributions. So the short array system on the single drone could be useful for imaging the shallow geological structures. So next question is how to obtain or conduct the long offset seismic experiment. As you can see, as I showed you in the previous slide, the 9 meter the offset data, how to obtain such a longer offset data to record the seismic refraction wave. So in such a case, we should use the several UAVs or the 2 UAVs, and we deploy the source and receiver for the different UAV. And one, I should explain in this slide. Yeah, and we use the 2 UAV system. Okay, and the source, one drone, one UAV have a source, and another UAV have a receivers. And if source repeatedly generate the same waveform, 2 UAVs can obtain the multi-channel seismic data with long offset. So in the first time, the source drone, source UAV generated the signal, and the signal was recorded by the UAVs. And this UAV moved to the next locations a bit far from the source UAV and record the source signal at the different locations here. And this kind of operation is continuous, is the repeat, this kind of the operations is the, how can I say that? Yeah, this kind of the seismic record is continuously conducted like this. So we can obtain the multi-channel seismic data like this, the schematic image, the one source and several receiver positions. So to conduct this kind of the multi-channel, the long offset seismic data acquisitions, we needed to increase the stability and energy of the seismic source. So we have developed the stable source system. So recently we have developed the stable source system. We call this system as a portable active seismic source system, PASS. So this is the picture. And in this system, the signal timing is accurately controlled. So stacking the continuous waveform enhance the signal to noise ratios. So this is the chirp or sweep generated by this source system, and we can continuously generate the same waveform. So as I showed you in the next slide, by stacking the several repeated signals, the signal propagate for long distance, so we can explore the extensive areas. And furthermore, by using the repeated signal, we can conduct the multi-channel seismic survey. So this is the final slide. So here I showed you the one example, how long the signal derived from the small seismic source system propagate. And this is a small source signals received by the distributed acoustic sensing. The vertical axis is offset and the horizontal axis is travel time. So this one is the one-shot record. Even the one shot, the signal propagates close to the 200 meters. But by stacking for the 60 times, the signal to noise ratio is significantly improved. So even this kind of very small seismic source system, the signal can arrive over than 200 meters. So the signal propagation in long distance, so the reflection and refraction analysis for deeper formation can be possible. And we can generate the stable and repeated signal so that we will be able to obtain the long offset multi-channel seismic data using the limited number of UAV. So this is a summary, but I think I do not have a time, so I finish my presentation here. Thank you very much.
Thank you. That was a really excellent overview of drone seismic surveys, and I found it particularly interesting how you take the conventional method of stacking and doing that now 60 times for drones, and you can get quite an interesting result there. There's one question that has come in here, which I will read, and then I think for the sake of time we'll probably have to move on. But the question from Alistair is, very interesting seismic survey. Have you compared results with ground-based seismic surveys?
Yeah. So yes, we can compare. We compared, but yeah, of course it's a similar result, but resolution is a bit different. And the short array seismic system, we mainly conduct the surface wave analysis so that we obtain the S wave velocity. So how can I say that GPR is how can I say that it's a kind of the image result. So yeah, of course I can we compared, but yeah, it's a bit difficult to accurately say we obtain the consistent result or not. Yeah.
Yes, thank you. There's one other question here that came in the chat, which I will read, and then we'll move on to our next one. It's a question from Bob, and it says, I'm confused about the geophone deployment. Can they be retracted so you can fly to another site?
Yeah. Yes. So honestly speaking, in the case of the Earth, we don't need to attach the geophone to the ground, because there is the air in the case of the Earth. So the floating position is also acquired the seismic data. But in this case, we attach the geophone to the surface. And of course, after this seismic survey, that we need to retrieve the geophone. Yeah, there is the motor is attached here, so we can attach and detach the geophone.
Excellent. Thank you very much for clearing that up. I think there's one question in the chat that you could type an answer to there, and we'll give it to Nathan to introduce our next speaker.
Okay, thank you, Takeshi. Great talk. Our next presentation is titled Design and Development of a Drone-Assisted Seismic Survey, and I'd like to introduce our next speaker, Johannes.
That's quite all right.
Cool. Right on, and I will present. So just briefly, my name is John Ryan Himes, and we'll be talking about this seismic survey that will be assisted by drone technology. And so we'll be just primarily focusing on that geophone placement process with this drone. And so even though active source seismic surveying has become an incredibly useful tool throughout a multitude of fields, there are some limitations to placing these geophone sensors. And the first being that if an area has incredibly sharp inclinations or rocky terrain, well, then it can be very hard to get personnel in and out of the area. Secondly, each geophone requires itself to be level and declinated in the area. And as your survey size increases, so does the amount of geophones that are required. And so we want to overcome these obstacles by placing them autonomously. But also a huge aspect of this project was to go off of pre-existing geophones. So those that already have the geophone sensors are able to transfer into this realm of automation more easily and readily. And so how we're going to do this is actually put the geophone inside of a geophone case, which we will mount onto a hexacopter drone. And that drone will be able to be sent out in the field, plant the geophone, and then be able to retrieve the geophone and come back home. And so as you can imagine, with a 2.75 kilogram geophone, it can become a hazard if this force-spiked object suddenly plummets through the sky. And so the design of this geophone case had to be extremely adequate and very meticulous. And so looking at it, we noticed that loading on this case comes from three entities: the self-weight of the case, the geophone itself, and the drone. At this point, we didn't know what material we were going to be using for the case, so we neglected the self-weight of the case until we determined the material to get a better understanding and then rerun calculations. We also wanted to better understand the scenarios that this geophone case will experience. And that comes in the landed scenario where the drone isn't turned on, the geophone case is being supported by the ground, and really just the drone is acting on top of the case. Additionally, you have next the takeoff and mid-flight, where now the weight of the drone is being supported by itself, and really just the self-weight and the geophone are acting on the case. And lastly, in the landing scenario, all three entities come together. The drone is pushing down onto the case, the self-weight is being pulled down, and the geophone is being planted into the stratum. And for each scenario, we wanted to look at how many ways it could fail. And so we looked at the reactions at the bolt connections to ensure a proper connection between the top and the bottom of the case. Next, we looked at the bending moment to ensure that flexural failure would not occur mid-flight. And lastly, we looked at the transverse shear stress. And this one was very material dependent, as we didn't know at the time that was going to be 3D printed. And you can imagine if it was CNC'd with wood fibers, that transverse shear stress would want to rip away from one another. So we wanted to look more in depth at that. So running the calculations without the weight of the case, it was found that the landing scenario controlled the reactions at the bolts and the maximum bending moment. It was very interesting that the mid-flight scenario controlled the transverse shear stress. Very similarly, in the top, we see that the landing scenario also controls the reaction at the bolts and the bending moment. And the transverse shear stress was also controlled in mid-flight, but with a higher value. It's also want to note that going back to that declination in the process, we also indicated a north symbol onto the geophone case so that a visual representation could also be made. And now lastly, we have the supporting rod components, which the bolts feed through and then connect the top and the base of the case. And it was assumed that as the drone is landing, it's landing level. So really the force is evenly distributed throughout each rod. And so with this assumption, we could follow the flow of forces and see that really the reactions at the bolts control the internal forces of the rod. Now looking at these values, they are relatively small, and this isn't just my civil engineering background, but really for this material that could be used, a multitude could have been used. And really we decided to 3D print the case because of the revolution that 3D printing is going through and is becoming incredibly convenient. When we handed the blueprints off to the shop, they actually estimated it to be 2 kilograms in mass, and we reran those calculations. And finding the allowable values, they were well above it. So we were in the clear on the case. And now we can start designing the drone system. With the drone system, we had to look at a lot of commonalities between shapes and also just if we're able to carry this pretty large payload. And so a common theme was that the all-up weight of the system was about 6 kilograms. We also wanted this drone to last multiple surveys. We don't want it to just break on the first one. So we went with carbon fiber components. It also needed to be carrying that payload, but we also wanted to be able to retrofit this drone with other technology in the future. So we went with a motor that was able to carry 2 kilograms, and with 6 motors being utilized, it has a maximum capacity of 12 kilograms. Leaving us with the all-up weight and the payload headroom of 1.75 kilograms. And so we also wanted to address the flight time. Talking to Iris Pascal, the local seismologist next to us, they indicated that they want about 30 minutes for their seismic survey. And this is great news for us because the drone really just has to go out, it can be shut down, save battery life, and then turned back on to come back home. So we looked at a proper battery to hold a 30-minute battery life. And also, as mentioned previously, the larger your survey size, the more geophones are going to be needed. And that means more geophone drones. So to avoid collision, we needed to implement some telemetry kit and some communication with each geophone drone to ensure there was no collision mid-air. And so now I'm going to be completely honest with you guys. I was hesitant to put this slide in, but I think it's very important to learn from our failures. And so when we went for our initial testing, the drone was able to go about a couple meters off of the ground, and we set it into a hover mode. But all of a sudden the drone started acting very strange, and it was trying to correct in the wind. And then all of a sudden it just headed straight for the one tree that was in our field. And so it did crash, and there was no injury at all because we were able to follow those safety protocols that were put in place beforehand. But initially we thought this was just user error, that one of us on the RC controller just accidentally flipped something. But talking to the pilot, nothing really seemed off. He just knew as soon as something was wrong, we flipped the kill switch, which has become a mandatory thing in all of our drones here at New Mexico Tech. But it was also brought to our attention that the NRAO was conducting FM frequency tests right next to us. And so this does bring up an important limitation with these automated systems, is that are we able to perform these close to urban areas or testing grounds without experiencing interference with our telemetry kit? And so with that, in conclusion, we do propose a system to automate the geophone placement. And going forward, we want to conduct more and more tests and figure out all of these problems and work them out so that we can compare it to an actual ground seismic survey and see if it is a proper replacement for these guys. We also wanted this project to be a viable option for those that already possess this equipment and be able to transfer to this autonomous realm more easily. Next step with the drone, talking about retrofitting, we want to add a camera to the top to visually monitor for any obstructions, unforeseen obstacles that the flight planner wasn't able to identify previously. And then even going further into the future and talking about our last presentation, if all three aspects of the geophone placement, the active source being activated, and data collection is automated, we have the possibility of surveying other worlds or parts of this world that we never would have thought of before. And so in conclusion, I really want to thank SEG and NSG for allowing me to present today. This has been an incredible conference. Just seeing so many brilliant minds present the research has just been incredible to me. But I also really want to acknowledge Dr. Akram from IRIS Pascal for allowing us to use the smart solo geophone that we designed around for the seismic survey and giving us advice on what they would like to see on an automated process. I want to thank Mr. Sebastian Moulton for 3D printing the geophone case for us and allowing this project to become tangible and even more of a reality. I also want to thank Dr. Isabel Morris and Dr. Mustafa Hassanalian for giving their continuous advice and guidance throughout this project and having my back throughout it. And on that note, I would like to open the floor to any questions or comments you all might have.
Thank you very much, John. That was a very interesting presentation and well presented, if I do say so. So thank you very much. I had a quick question just while probably people are typing into the chat there. In terms of maybe saying taking a passive seismic sensor, which is the idea is you take the seismic sensor, place it somewhere and leave it for a period of time. Do you think from an engineering perspective, you could rig up a drone to be able to carry one of these, place it down, come back to a base station, pick up another one, and go out and set up an array of them that you could then leave for a month and then it could automatically go and pull them back, sort of thing? Do you think that's something that we would be able to do?
Most definitely. That would be incredible too, to incorporate the passive aspect to it. I think we narrowed in on the active source primarily because in the mechanical engineering department here, they are working on an autonomous drone that's inspired by dandelions rolling down the ground to create that seismic source. And so they wanted to work in conjunction with us. And so that's why we focus on the active. But most definitely with the technology that's out there, that would be incredible to have a docking station and a retrieval station for passive tests.
Or I know one of the other things that has come up is, you know, having them deployed or then even just having a drone fly over the systems and having it Bluetooth the data to it or something like that. I've heard of systems doing that where you can use the drones to be able to collect the data and stuff like that. So it's definitely very promising. Drones can be used in all sorts of ways to solve these interesting solutions. I particularly like the engineering aspect, so thank you very much. If anyone does have any questions, you can place them in the question and answer period there and stuff. Otherwise, if anyone of the panelists have any questions, you're welcome to unmute yourself and ask directly. give it a sec here to see if any roll in. Well, I had one other question with this then. If you, from an engineering perspective, what do you think like the next big challenge will be in kind of further developing this, or where do you see it going, and how could you overcome this from an engineering perspective?
Well, I'm very, very fascinated with the materials aspect with it, and with the balloon going to Venus. I thought that was incredible. Because that's the biggest thing. The surface area is incredibly hot, and so just translating environment to the material aspect of it and the strength of materials, having to adapt like that, I think is going to be the next biggest challenge. I think the idea of a drone will have to be reevaluated, and we'll have to look at other methods for powering these systems, as sometimes the temperatures are way too hot to be able to carry a LiPo battery without physically melting it.
Thank you very much. Yeah, again, excellent presentation, and we'll stick around for the discussion at the end if anyone has any further questions. So with that, I will pass things over to Nathan, who can introduce our next speaker.
Sure. And John, I will say I feel for you on the crash, and thank you for keeping that slide in there. It's always good to be reminded of what we learn when things don't go as planned. And we had a little bit of a discussion yesterday about crashes and pilots, and there was a whole hand-raising exercise for people that had not been in a crash, because I think that would have been fewer people. So anyway, it's never fun, but you know, you're earning some street cred with that one. And okay, so unless someone has other questions, I think I'll go ahead and introduce our next speaker. His title for his presentation is Freefall Sensor Development by UAV Fleet, System Integration Pilot. And I'd like to introduce to you John Archer.
Good morning. I'll just share my screen. Can you all see that okay?
Excellent. Yep. Yes, that's perfect.
Okay. Yeah, I'll be talking about Freefall Sensor Deployment by UAV Fleet, System Integration Pilot. So this is actually going to be the latest METIS pilot test that we carried out in June. And I'd like to acknowledge my co-authors, Malcolm Gregg and Brendan Chambers. So I'll talk a little bit about METIS for those who are not familiar with the project. And I'll talk about some of the previous pilots that we've done, just to give you an indication of what we've already de-risked and why we're just concentrating on one aspect. Which will be the goals of this particular system integration pilot. And then I'll go through the different components that we've tried to integrate, including the safety clearance system, touch briefly on the authorization process, because that can be very time consuming, and then just touch a little bit on the results and the conclusions. So in 2015, Total, now Total Energies, motivated by the high cost and the poor quality of Foothill seismic acquisition, decided they wanted to revisit these challenges, in particular to look at using the advances in drone technology to drive improvement, especially related to the deployment of receivers, kind of what John was just referring to. And that was back in 2014, 2015, and I got a short video introduction on that, which some of you may have seen, and apologies if you have.
The METIS R&D project was launched in 2014 in order to tackle seismic acquisition in hard-to-access areas. It aims to reduce fieldwork to a minimum by sending drones to identify zones free of humans or animals and to drop darts. These darts are fitted with a sensitive sensor and a radio emitter, allowing instant data transmission toward a central antenna.
So the first major pilot we did was in Papua New Guinea in 2017, and the goals were basically to automatically fly a single drone beyond visual line of sight above the jungle canopy, launch, I believe it was 60 to 70 darts above predefined sky holes, assess the penetration and their coupling, check the seismic signal quality. So we actually wanted to record a seismic source into these, and then evaluate their communication back through the rainforest environment to the central recording system. And again, I've got another video of this.
Once assembled, the darts are loaded on the drone, ready to be launched above sky holes in the canopy previously mapped on LiDAR data.
So we ended up dropping a total of 62 darts over the course of this project from a height of 50 meters.
Everything goes to plan, and operations run smoothly. Rapidly, the 4 darts are dropped, and the drone comes back for more. Mud guns are used as sources, and the first seismic traces are measured in real time by the METIS system. The METIS pilot is already a success.
One of the principal goals of this program was to determine if we can drop darts from a drone, have them land in the jungle, communicate with them, shoot seismic data into them, and then recover that data. We demonstrated this yesterday.
So one of the issues we had 8 bad landings in that out of the 62 darts, and a little over 50% of them managed to communicate back to the central recording system. So then we switched to the desert for the second pilot, and that was split into 2 phases. Phase 1 we completed in 2020, and the goal of phase 1 was in fact to de-risk the technology for a larger full 3D seismic project in phase 2. Unfortunately, COVID intervened and the second phase was never acquired. But I do have a short video clip on phase 1 which goes through what we did. So during the course of this project, over 6 days, we dropped 223 darts. 91% of them planted in the ground, 9% failed to. However, of the ones that planted, the majority of them had a tilt greater than 15 degrees from vertical, which is not acceptable for us in terms of the geophone performance. And we did some aerodynamic analysis, and we determined that they were being affected by the strong winds. And so we had to redesign the dart shape. However, the communications were improved. We had 85% that managed to communicate successfully with the central recorder after release. Now, we also compared the dart on the left with a buried geophone on the right in the same location, and we had very similar signal. Obviously, the dart's a little bit noisier, as you can kind of see there on the left-hand side. So that brings us to the system integration pilot that we carried out in France this year. And the main goals here was, in the previous pilots, we'd used a single UAV to prove up the individual aspects of the system. But in order to get the productivity that we need for a 3D seismic survey, we need to scale it up by deploying from multiple UAVs simultaneously. So our principal objectives for this demonstration were to test the new UAV design and its operation in swarming mode, then integrate 3 control systems, each developed by a different METIS partner. And then we also needed to demonstrate that we could drop a payload from drones in a safe manner, which would be essential to obtain the authorization to fly from the French Civil Aviation Authority. I'll go through the following system components: the UAV fleet, easy chains, then the ground control station, and finally the command and control. The Bumblebee UAV was designed and built specifically for METIS by ISS Aerospace out of the UK. The maximum operational takeoff mass is 35 kilos, so it's a big beast, and that's with a full payload of 6 darts. It's a 4-arm, 8-rotor design, push-pull, counter-rotating rotors on each arm, and it's got a span of 2.2 meters from prop tip to prop tip. It's designed to fly with a failure of 1 rotor. Some of the additional safety features include a LiDAR proximity launch override, dual LiPo batteries for power redundancy, multiple redundant nav inputs, and redundant control systems in case of emergencies. And the geophysical sensors are contained in a removable smart cassette with, again, multiple redundant safety systems to prevent accidental dropping. So the primary release system is a lock at the tail of the dart. Then we've got a secondary pincer lock that secures the dart in the tube as a backup system. And then finally, a little fork sensor which determines that the dart is actually deployed successfully or not. All of the loading, lock, and sensor errors are caught in advance at the loading bench, as opposed to us finding them out when they're already in the air. Okay, moving on to Easy Chains. This is a flight management system that was developed by Scallion, another one of the Metis partners, to determine the trajectory of the UAVs in real time. So it allows them to fly autonomously during normal operations, and the pilots are really there just to intervene and take control if absolutely necessary. The software runs simultaneously on a ground system and also on a Raspberry Pi within each UAV. And the ground-based algorithm receives the mission data that we send it from the command and control, which includes all of the receiver locations, the drop points, we call them, geofences, corridors which cross geofences, and then optimally allocates drop locations to each UAV at takeoff. And then the airborne algorithms then determine the best flight path to reach the assigned drop locations, taking into account any geofences and corridors, and then exchanging information with the other UAVs in the fleet in order to avoid collisions or traffic jams. The ground control station was developed by Altran, which is part of Capgemini Engineering now. This is the principal means of human interface with the fleet. So it gives us two operator controls. You can see on the left, we've got the swarm screen, which allows the GCS manager to receive status updates on the fleet. You can send individual commands to particular UAVs. And on the right, we've got the dropping console, where an operator reviews the images received from a drone when it's on location, and he analyzes those to make sure it's clear of obstacles prior to authorizing a drop. The command and control manages the larger environment in which the fleet operates. So this is really the connection with all the other aspects of the seismic crew. It's a database-driven GIS system with all of the maps and source and receiver locations, obstacles, etc., that comprise a standard seismic operation. And then we combine this with a real-time interface for receiving and processing streaming information. So that is positions of personnel, positions of vehicles, other aircraft, the UAVs themselves, and so on. And we also have a back-end interface into the Easy Chains program so that we can update the fleet of any events that might impact them during an active mission. The command and control also includes a mission builder that will take an entire seismic project of receiver locations, infrastructure, and so on, and then splits them into little bite-sized missions for uploading to Easy Chains. We have location tracking of all the personnel on the crew with SOS and two-way alert capability. You can see the pictures of the people there on the job in France where they're standing at any one moment. And then there's a protective bubble around personnel or intruders if they stray into the mission area. And that protective bubble also gets uploaded to the fleet so they don't overfly. We have a mobile app as part of the command and control, which we give to the crew so they can accompany and they can also communicate with other crew members and perform some other activities. There's integrated push-to-talk communications with a bridge to the handheld radios that the crew are using for the rest of the seismic operation. The dispatch channel for journey management, integrated procedures, checklists, work instruction tools, and so on. So moving on to the safety clearance system, in order to be able to drop what are potentially lethal payloads from a drone, we use a multi-layered approach to ensure that basically third parties are first deterred from entering an active mission area. If they do enter them, we must be able to detect them either on the ground or by air. And then that detection should trigger a series of actions that minimize risk until the intrusion can be investigated. And then finally, if somebody does slip through all of that, then we also need to have a way to prevent the actual dropping operation itself. I'll go through these in turn. So this was the public awareness campaign. This is the very first time that the French Aviation Authority had issued an authorization to fly for this kind of mission where we're dropping items from drones. And so we erred on the side of safety. We flagged the entire area with caution tape and signage explaining that it was dangerous to enter. Plus it was private land. And we also alerted all of the people who were living nearby. Regarding the ground detection system, as well as carefully placing guards and observers around the area, we also deploy an electronic network of sensors. So you can see the passive infrared sensors in the top there. Those are used to detect incursion by third parties or animals along paths or tracks where we don't have direct line of sight that might lead to the mission area and give us some early warning. Now, as I mentioned, all of the crew are wearing those trackers. You can see they have special vests and the tracker goes in their vest. And then that is connected by a LoRa network to the command and control. The surveillance UAV works in conjunction with the dropper UAVs. It patrols a predefined route around the mission area, and it provides an aerial platform for intruder detection and perimeter monitoring. And the intention is that the surveillance UAV will spot potential intruders while they're still way outside the mission area. And then at each defined point of interest, then the SUAV will stop and it'll take a series of photos scanning a particular range. And then those photos are then verified by the pilot as they come in on his remote control handset. And then simultaneously, they're analyzed by an onboard AI detection system, which is looking for intrusion events, whether those are people, vehicles, or animals. And if an intrusion into the mission area is actually detected by either the ground or the air systems, then the cassette lock is automatically activated, preventing any further dart drops. In addition to that, a dynamic geofence is created at the location of the intruder, and that is uploaded to the fleet, which then prevents drone overflight over that particular region. While this is going on, the mission superintendent can order a hold your position across the fleet to suspend operation until the ground detection team are able to get out there and determine what actually happened and then provide additional instruction, whether to come home or whether to go to an alternative helipad or whether to continue the mission. Finally, if everything else fails and we're actually ready to drop the UAV, then there are 4 different approvals required for the dropping stage. The dropper UAV, as soon as it arrives at its location, it sends a series of images of the drop location to the ground control station and also simultaneously to the UAV pilot. The dropping operator will review the images by zooming in and out until he's convinced that the area below the dropper is clear of intruders or other obstacles like rocks or bushes. And once it's clear, then he authorizes the drop. In addition, the UAV pilot must give his authorization if he can see that the area is clear. And an onboard AI system also analyzes the imagery. And then finally, the dropper itself has got certain attitude restrictions that determine whether it's sufficiently stable to allow the drop. I won't go into this much, but in order to perform the demonstration, we needed permission from the French Aviation Authority. This was managed by Altran and involved preparation of hundreds of pages of documentation and submission of 43 separate supporting documents, including operation and maintenance, training manuals, emergency response plans, risk assessments, drone test reports, and so on. So finally, the results. Again, a short video. So the demonstration occurred over 2 weeks in June this year. Because of COVID, some of the people weren't able to make it. My 2 co-authors, Brendan was stuck in Vancouver, Canada, and Malcolm was in Houston. Fortunately, they managed to connect using the command and control app with the push-to-talk comms. And so they were able to operate their aspects of ground detection and mission superintendent remotely. It was actually the first time we flew all 6 UAVs together. And the system integration was successful. We did quite a few dry runs before we actually went out into the field remotely. The ground detection system comprised of 5 observers. We had 20 infrared detectors around the area on pathways and tracks in the forested area. And we had more than 30 trackers reporting positions every 10 seconds, typically, of crew members and visitors. We did a lot of the test drops at 25 meters. That wasn't actually high enough for the darts to stick in the ground. And so we actually dropped at 50 meters for the final test run. At 50 meters, they all managed to stick the landings. We had no safety issues. We did have one hard landing when a prop broke, but there was no major damage. We had some minor communications issues, some problems with cameras. We had some darts that were stuck, but most of these issues were fairly minor and were sorted out. And in terms of deployment productivity, the best we got, we weren't really aiming for high productivity in this test. It was really more about proving that we could do the system safely. But the best we got was about 101 drops per hour, and that was using 3 droppers. This is a drop from 50 meters. Okay, so to conclude, we successfully demonstrated the integration of the 3 system components, which allowed us to safely drop the payload from the drones, doing it while using a fleet of multiple drones in swarming mode, and then also do it in a fully autonomous manner with the pilots just there as backup. Another positive note was that we did receive the first authorization to fly from a European Aviation Authority for this kind of mission. And the next steps, we definitely need to improve the efficiency, as I mentioned, and reduce the headcount. And then there are certain challenges to be faced in determining or finding funding to get this through to the next stage. And thanks to the METIS partners, Scalian, Altran, Capgemini, Total Energies, ISS Aerospace, and RPS. Thank you.
Thank you very much. That was a truly spectacular overview of the systems you've developed and a lot of the safety concerns that you have to consider moving forward with this, especially with risks and things. I'll open things off with a couple questions that have entered in the chat here. Again, please start putting your questions in the chat and we'll read them out here. The first question from Gary Young is, first, how are the geophones retrieved?
So in the test that we did, the geophones were retrieved manually. In the phase 2 that we were planning to do in the Middle East, Total actually developed a remote surface autonomous vehicle, 6-wheel drive device that would pick them up in the sand with a scooping device and then move them into a rack at the back and then bring them back autonomously. We didn't actually get to test that in this, but I do believe that they did a separate set of tests in the sand dunes along the French coast, and we seem to be quite happy with it. And then in the future, to be honest, we're not 100% convinced that dropping by dart is the way to go, and we think that we should be able to drop by drone and retrieve by drone, and that's really what we're looking at next.
Excellent, thank you. And the second part to that question is, are there plans to integrate with sources and actually do seismic surveying?
Yes, well, there are. So we also have another source, which is called the Elephant, which is a new seismic source, which is also autonomous surface vehicle. And the idea was to use that, but especially well suited for deserts and open areas. Not so good, obviously, for the jungle. The jungle, we didn't actually come up with a decent source, so we're pretty much stuck with continuing to use drilling and dynamite. There are a few contenders, but they're not really suitable for the very short time frames that we need to match the battery life of the darts. I hope I explained that sufficiently.
Yep, no, that was great. We have a question from Jeff that says, great advances, cost, productivity benefit, potentially compared to manual systems for different terrains?
Yeah, so I mean, this is my big issue. There's no point doing something if it's not going to be cost effective. And right now we're nowhere near there. You know, the head count, we had over 30 people on this demonstration. But obviously this is very early days and we're really just trying to get things through the regulators, and efficiencies will improve. So we've gone through the numbers and we think that we can get a more robotic automated system where each person on the deployment crew can deploy 2,000 receivers per day per person. So a crew of 2 can do per shift. So a crew of 2 can do 4,000 in a shift. And then it starts to get quite cost effective because they can do that over all sorts of terrain. It doesn't really matter whether it's steep sand dunes or whether there are rivers or ravines crossing the way or whether there are fences or pipelines. It doesn't affect the drones. They just move at the same speed.
Great. Yeah, there was a comment in the chat here as well that said having high safety standards helps with the acceptance of drones, and I think particularly for this application, I mean, going to the lengths that you had to, you know, to write as many reports to get permits and things like that, I think this is really the right way to go about something a little more risky like that. To that point, I was kind of wondering in terms of like the risk factors with dropping these sorts of darts, like, do you try and do it quickly so there's less exposure and time for people to kind of walk into the area sort of thing? So maybe drop within a 10-minute period of time rather than over like an hour to minimize that exposure time? Or I guess what's kind of, in terms of risk to the public or anything like that, what do you see as the biggest challenge there?
Yeah, one thing I didn't actually show is that we didn't, but Total developed a risk assessment tool, which we plug in a whole bunch of different factors, you know, what the population density is, what the movement of people is throughout I mean, this is really not designed for built up areas. And this is really designed for very remote areas, but you still get people around or animals and things. And you can plug in the population density of the place you're working at, and you can highlight areas where there's going to be greater transit or movement. And then you place your different observers around, you do view shed analysis of it, you put in where your different sensors are, and it comes up and it gives you what are the chances per flight hour of there being a hit, somebody getting hit with a dart or something getting hit with a dart. And we have to be at less than 1 × 10⁻⁶, so less than 1 chance in a million per flight hour. And we found out that the best way to do that is to deploy at night. I didn't show the video, but we do have quite a good video of a night deployment that we did in Abu Dhabi using the infrared as the camera, and it's excellent. It's really good visibility with the infrared. And of course, there's nothing out there. There's no one wandering around the desert at night. And in fact, most parts of the world at 2 o'clock in the morning, you can be pretty sure that it's a good place, and the wind is typically quieter and most of your crew is asleep, so it's just it makes sense to do most of the deployment at night.
And with infrared, that seems like it would be easier to see wildlife.
Exactly, much easier to see wildlife, especially if you've got things like you know, vegetation, and you get a better temperature difference across at night than you do at daytime.
True, yeah, that is, like I said, spectacular, because that hits on a lot of, I know in our department at Queen's, they do like rockfall analysis, and you've hit on a lot of the points that they discuss there, you know, determining that risk and really quantifying it and make sure you're below it. So I think that's amazing for the drone technologies, where we all know that the risk of having crashes is up there. So amazing. I think there's one more question that's popped into the Q&A here, which I'll answer, and then if no more come up, we'll probably shift over to the discussion period after that. But the question reads, with these receivers, do they have the same recording potential / capability as current node receivers?
Yeah, these are standard geophones. So what we've used are standard 10 Hertz geophones that we have in our regular nodes. But we don't think that's the way to go. We've used the geophones, but as you saw, that they're quite sensitive to tilt, and we're looking at the next stage moving to 3-component accelerometers. and then we don't have to worry about tilt, and it also opens up a whole bunch of additional possibilities that we don't get by using the geophones. So that's that would be the next stage, if there is a next stage, that's the direction we'll head in.
Excellent. Well, thank you very much, John, for that insightful presentation. And I guess, Nathan, is there anything else you would like to add to things? Otherwise, I think we will transfer into the active live discussion, where we have had talks today from different EM methods, seismic methods, fleet operations, safety concerns, balloon operations on other worlds, and things like that. So if anyone at this time has questions, you can either type them into the Q&A if you're able, or you can raise your hand and unmute yourself, and we will facilitate the beginning of this.
Yeah, thanks, Callum. And I did have one question/comment for John. Just seems like a really sophisticated system, in that you've really had to tackle a whole bunch of issues here with it, especially the kind of the algorithm building for autonomous fleets, you know, going out and dropping the darts and not running into each other, not running into people, or flying over people before they drop it. So I guess really just kind of was impressed with that part specifically, and just was going to ask, you know, if it just seems like a lot of work was put into something like that.
Yeah, it was a lot of work. So Total, as I say, they started it in 2014, 2015, and they've, well, I'm not allowed to say how much they spent on it, but they definitely had a much bigger budget than we would normally get. And the unfortunate thing is that they moved their attention away from land to marine, and then with the recent changes, and then with COVID, that was pretty much the end of the program. So they are no longer investing in METIS. Their investment has come to an end. And SAE, the company that I used to work for up until last week, have just recently divested of their R&D department. So they're not pushing it either. And so basically we're at the stage now where it's almost orphan technology. I mean, it's not just something that can be used for seismic. I mean, this is basically logistics. You're deploying 1 kilo packages from drones autonomously at very high levels in a safe environment. So there are so many possibilities, and I really hope that it gets picked up by someone else for seismic. The numbers that we've looked at are very appealing. We can reduce headcounts enormously. We can get people out of the field. We can make it a lot safer. But it is an expensive business, and it's going to take somebody with quite deep pockets really to get it to the next stage, to make it commercial.
And I see that mobile app being really useful too. And you know, a lot of that technology that you've developed could be applied, like you said, to other types of missions, not just like this one here. So.
Yeah.
And by the way, people should be able to speak over the comms now, even if you're not a panelist. So, of course, raise your hand and be polite, but yeah.
I do see there's one question in the Q&A here from Mel for you again, John. It says, how does your DART development risk threshold compare to typical seismic deployments? It seems quite risky.
Yeah, well, this is actually quite surprising because the biggest risk for any seismic operation is road transport. And if we can get people off the road, if we can get people out of the field, then we're reducing risk. And we massively cut down on the headcount with this method compared to people walking and doing manual planting. So we think that overall it's a big uplift in the HSE side of things. But yeah, we do have to be very careful. As I mentioned, it's not for everywhere. I certainly wouldn't want to do it in a place which is built up. I don't think the productivity would be there. It's not to say it's impossible, but I don't think it would be worth doing just because your productivity would be so low. it would be easier to go out and do it manually.
Thank you very much. I see that there is a question in the chat here that says, is there any new solution for drone flying longer? And I don't know if anyone in our audience here has any expertise with some longer flying variants. I know just off the top of my head, there's hybrid options that are out there, gas hybrids and things like that. But maybe if there's someone who has some particular experience with this, if they could, yeah, touch on that.
Well, I don't mind adding that that's one area that we're currently working on, testing hybrid systems, primarily for fixed-wing aircraft, but we've also utilized them on rotary wing vehicles. And that essentially gives you flight times anywhere from 2 to 6 hours, depending upon the type of propulsion system that you have on there. It's still a gasoline engine driving an electric engine or electric motor.
Callum, can you hear me?
Hi, Dennis. Yes, I can.
Yeah, we've done the same with a rotor system. It's a hybrid, and we put on a really skookum motor on it. Very light, very powerful, so that it can. It's got long duration. Plus, it can do a lot of good climbing in mountainous terrain.
Very interesting. Yeah. So that's a single rotor you were saying there. That's gas powered. A multi-rotor. Okay.
Multi-rotor.
Yeah, I definitely.
It's a Foxtech frame.
Okay.
But with modified a lot.
Gotcha. Yeah, I know with the hybrids, when they first started coming out, I was very interested in that because obviously, when I think I first started doing mag research in 2016 sort of thing, we were lucky if we would get 10 minutes of flight time with some of the 2 kilogram systems we have. Of course, drones have come a long way since then, but it's really interesting to see kind of these bigger systems and some of the hybrids that will be moving forward. Yeah.
I might add that there's one drawback to a hybrid system with an engine on board, is it's noisy. And you can't be disturbing wildlife. We operate in remote areas, but there's still lots of wildlife in remote areas, and we can't be disturbing caribou herds or anything like that. So there are some limitations.
Yeah, for sure. The cost to benefit to that. All right, we have, I think we'll switch topics here because I see a hand up. Alex, if you want to unmute yourself and ask your question, we'd be happy to.
Yeah, that was actually on the same topic there. Dennis, I was just curious if you do have any hybrid experience with fixed wings. How did you, aside from just noise levels, did you find, how was the noise from any generators in some of these EFI engines?
Well, it's a single engine, and it is quite quiet. It's very quiet, actually, but still, you're flying. You can't be flying over a herd of caribou, and it's not a fixed wing. It's a rotor, multi-rotor.
I'd love to open up the floor to anyone who has done work with those hybrid EFI engines. Just curious about really the noise provided off those generators.
I'll take a stab at what I think might be going on with it, but I don't have any direct experience with data collection or anything like that. But my understanding with them is you just have like a gas or kerosene powered engine that feeds into, either a 3-phase permanent magnet synchronous motor or a BLDC motor. And my guess is the signals from that, depending on the size of that motor, would be pretty similar to some of the characterizations that have been going on of the drone motors as well. Obviously, if it's not particularly the exact same type of drone motor that's being used, then there might be some different relationships going on there. But my guess is it'd just be a more powerful signal, but kind of along the same lines where you would see, you know, the mechanical rotation of that motor as well as the different permanent magnet signals as it rotates around too, and then the induced magnetic field signals. But I haven't been able to get my hands on one of those generators yet to kind of look into that, but definitely is an area of interest. Does anyone in the audience have any experience with those or characterizing hybrid generators as opposed to motors?
Thomas, Stanley Jones here. I've years ago was involved in some testing with a balloon mounted EM system and with a generator on board, and that was problematic. Since then, planning to do testing this month with Skyfront drone with our own mag sensors as well. I'm told people do it, but somewhat skeptical as to how clean it will be and how much further away from the drone will have to be. One advantage I've heard is that the generator noise is consistent as opposed to motor noise, which varies with turbulence and whatnot. And so it should be easier to filter out from a mag perspective.
Yes, excellent point. Thank you for adding that. If there isn't anyone else that has any thoughts on that, please feel free to cut me off at any point. I had a couple questions just regarding kind of the balloons and things like that, because that's something I'm new to, but I noticed that you're kind of launching them on sunny days and stuff like that. I'm just wondering if our speaker that gave that talk could comment on that. Like, is there limitations to when you can launch these sort of balloon systems, or whether you know, you can do it kind of all the time?
Yeah, it's a great question because for the solar balloons, you know, it does require some solar radiance to be able to heat that up. So for a ground deployment where you're inflating on the ground, it does need to be on a relatively sunny and low wind day as well. You know, if you're getting winds in, say, the 5 to 10 mile an hour range, you know, that becomes problematic to be able to launch these. But that's where the Grand Slam launch comes in, where you're able to launch it using a standard weather balloon. That was the video that I skipped, where it takes it aloft. The weather balloon bursts as normal, typically around 90,000 feet. And then as it falls back, it ram air inflates the balloon and heats from there. And typically either way, you'll end up with a float altitude around 60 to 80,000 feet, depending upon the size of the balloon and the payload weight.
Thank you very much. That's interesting. One other question, just while we're on that topic, so we don't jump around a little bit too much, was I was wondering, just like for the Venus kind of landings into the atmosphere and stuff like that, that'd be quite a little bit different than, say, landing a rover on Mars or something, as we've all kind of seen in NASA's videos. I'm wondering if you could just talk on that a bit, because it seems pretty interesting. Like, how would you just kind of launch the spacecraft into the atmosphere, slow it down enough that the balloon can just start floating, sort of? Or
yeah, it depends upon the mechanism that you're using for that. And I'll just, you know, share the screen here if you don't mind, and just show a picture of that. But this is the concept for that basic deployment. It's not a high resolution image, but you kind of get the feel for that. So your re-entry, or your entry into the atmosphere, is very similar to what everyone is seeing on Mars with the Curiosity and Perseverance probes or rovers. But instead of going all the way down to landing, you start to descend under a parachute, and then that's when you do the inflation. And so this could either be a ram air inflation, or if you're using something like a buoyant lifting gas like a helium, then you could do that there. And most of the proposals are focused on chemical reactions, so very similar to what you would have you know, with an airbag type of inflation. But that would be the basic process.
fascinating. Thank you very much for sharing that. I'll remind people again, if you have any questions about anything that we've discussed today or anything like that, feel free to raise your hand and ask them directly. Otherwise, I think there is a question in the chat here, which I'll touch on, and it says, does anyone have experience on getting rid of UAV-related EM noise? We've seen that one approach has been extending the sensor, but has someone tried to predict or remove the noise actively? Example, using UAV information like rotor currents, battery voltage recordings, etc. And I could go on for this for a while, but I think I'll let anyone else take the floor, and I'll jump in a little later because you've probably been tired of hearing my voice. So I guess if anyone has any thoughts on how to remove this or has moved forward with doing this, the floor is yours. And I see Gary Young has his hand up, so the floor is to you. Unless you had a question.
There, I think I was muted, sorry. I haven't seen anyone in this program talking about the EM61, but Geonics does have a unit that they fly, and they do have an intervening coil between the measurement coil and the instrument for the purpose of bucking out the noise produced by the drone itself. And Ron Bell and I are going to be trying that here in the next few months on a project that we're going to be working on.
Fascinating, awesome. So actively trying to remove this the noise through the use of a bucking coil. Very, very interesting work. I look forward to hearing about that. Anyone else have any thoughts on this?
I don't have direct experience filtering it out. This is Thomas here again. Helicopter collected data that uses a mounted system on the helicopter. We found tends to be noisier than ones that are towed. But for the, and then that has gone with systems flown by drone as well. The further down it's dropped, it's far, far cleaner. But to be able to do it from the drone, I haven't seen it successfully done yet post-processing. One of the limitations has been that to do it well, you need very high frequency data. And to deal with that much data over many day survey, it becomes the processing involved is quite significant. So it just adds to the work without the benefit. Maybe in certain situations they could be worth it, but just dropping the sensor has always been the easiest option for us.
Yeah, and I guess I'll build off of that just with kind of the experience that I've done. And what a lot of my research focused on was trying to characterize the EM noise from the electromagnetic motors themselves, and what I was able to determine through my research, and this is not by all means the full story of what's going on, is that there's quite a lot of different signals, typically starting around 50 hertz, which is the mechanical rotation frequency, so the frequency at which the rotor actually spins. And then you can go all the way up into the tens of kilohertz in terms of some of the magnetic and electromagnetic signals. And that's the point that Thomas just pointed out. It's very hard to be able to collect, tens of kilohertz data to precisely know what this is for each individual drone system and stuff. So some of my research has looked at trying to predict what these signals will be, but the problem with this is, of course, if you're running, say, a mag survey like I would do, you might be running at 10 or 20 hertz. You're going to have a whole bunch of different alias signals that are going to be put back down into your lower frequencies from all these rather strong high frequency signals. So this seems to be the understanding right now, sort of the state of the art of trying to suspend your sensor low enough that you're not sensing all these alias signals and raising your noise floor within the frequencies and wavelengths that you would be interested in. And that seems to be the method that most people have gone forward with. with doing this. So yeah, if anyone else has any points on this sort of stuff, speak now, I guess. Otherwise, we can move on if anyone else has any other questions or comments from the talks.
So far, thank you very much for your impressions. Maybe to add something else to this topic. I mean, what else could be possible is maybe a way of shielding your drone and your sensors. So I was also like maybe imagining some kind of shield where you put your shield directly beneath your UAV and try to shield as much as possible to the sensors. So maybe someone has done something like this already.
Yeah, I think one option I've seen is, you know, you can take the wiring inside the drone and wrap the wires together in a way that minimizes the magnetic signature that's being sent through there. So that's one thing I've heard that haven't been able to compare the results, but seemed like kind of an ingenious idea.
Yes, yeah, I understand. This is, I mean, typically you try to minimize these effects by like putting the cables all together and this, to be able to minimize this radiation as much as possible. And yes, I mean, as it was said also that this is very difficult if you have 5 Hz recordings from drone information. It becomes impossible to high frequency noise.
Yeah, the shielding point you brought up is a really good one, because I've thought about, I haven't really done too many experiments with looking at, say, things like mu metal to be able to potentially shield some of these signals, or start to think about ways of engineering solutions for this. But again, when you start going that route, you're adding, you know, weight to your drone and decreasing payload times, and there's not a real clear way in my mind of how you would actively be able to do that. But it's definitely an area of research that you could try and move forward with, is yeah, shielding these electromagnetic interference signals.
Yeah, I thought there are also some mu metal tapes or something like this, which are not very heavy. So I mean, because it's problematic if your shielding is too heavy as well. This is not very nice. But yeah, this is definitely a point where yeah, where some experiences and some maybe new ideas can bring some new yeah, new techniques.
So we've got a comment from Gary Faraday Cage, question mark. Neat idea. Brings up questions for me, like, you know, if we shield too much, we may not be able to use the navigation sensors on the drone. But if we could pick, you know, just certain parts to shield and not to shield, you know, maybe Faraday cage concept could be used there.
Or maybe there are some approaches to distinguish between noise coming from above and noise coming from below, because typically you're not interested in what is coming from above. So, I mean, you can, I mean, but you can try to shield your sensor, but this is not what you want, because you're interested in this frequency band. So caging all or shielding all is not the approach. You have to try to somehow distinguish where's the noise coming from, and as far as you know this, you can maybe try to say, okay, this is clearly UAV noise, and then say, okay, we just remove this or filter this somehow out.
And it looks like Jeff has some questions for Takeshi and John Archer.
Yeah, thank you. For Takeshi, my question is on the endurance of your system. How many seismic spreads feasibly could you do with one battery change? Maybe take that question first.
Do we have Takeshi?
Yeah, I was just looking through and I don't think I see Takeshi in the list here.
Okay.
It may be middle of the night for him.
Yeah,
that is true.
That's true. My other question is for John Archer. I mean, I've been involved in bird dogging a 3D seismic survey, and it's not just a technical exercise. It's a people and farmer engagement type exercise. So there's problems with getting the big vibrators onto the property, and then at the moment with the manual system, there's probably no risk or very little problem with the manual deployment systems. So it seems to me that there's a big community engagement issue with getting farmers to accept, even if the French authorities or the authorities say it's safe to deploy darts, there's probably a big community engagement problem in getting farmers to sign on to having darts being dropped in their properties, in addition to the damage that seismic vibrators might do to their property, even if they're compensated for all that damage. So that's one thing, and the other thing would be getting the seismic contractors on site as well. Has that been thought about? It's one thing to have a technology, but then getting people to accept it. Has all this been thought through? And I'm interested on your comments on that.
Yeah, so a couple of things. So first of all, it's really designed for places which are pretty hostile, where you don't really want to have people out in the field working. So that's either places which are very hot or very cold. Think of North Slope, think of the desert, think of the jungles, think of foothills, where there's not a lot of people out there that you have to worry about. That's really where it's ideal. As I mentioned previously, I don't think that I would be inclined to take it in somewhere where there's a lot of people. However, having said that, we also think there's a better way of doing it rather than dropping these darts from 50 meters. We think that a low altitude approach is actually more suitable. I think everything would basically be scaled down. We could still use all of our systems that we've developed so far, but we'd end up not dropping something which is lethal. And when you're dropping a lethal payload, that's when you have to be pretty concerned. But if it's non-lethal, if it's just something that bounces off you and maybe hurts you a bit, but it's a totally different story. And then suddenly things kind of open up a little bit. I still don't know if I'd want to use it around farmers because they're not a lot of fun, even at the best of times. But it's an option. And then your third question about the seismic contractors. Well, I work for a seismic. Well, I used to work for a seismic contractor, and they are extremely conservative people. It's very hard to get seismic contractors to do anything which is different from the ordinary. So again, I think if this is going to catch on, it's definitely going to catch on in a place which it's just obvious. It's a no-brainer to go ahead and use it, and which is why Total initially was starting with Papua New Guinea, because it is the most expensive seismic in the world there. But we definitely see a big cost saving and a big efficiency saving and a headcount reduction using it in the desert as well. So I think that's probably going to be more of a commercial location for it rather than the jungle. I hope that answers some of your questions, Jeff.
Yeah. No, the other question was the systems that I've worked with. They generally deploy an array of about 6 geophones rather than a single geophone. Is the seismic processing technology able to do that spatial filtering now without having to deploy multiple geophone arrays, or do they just they can work with a single geophone? Is that what you're saying?
Yeah, most parts of the world, people have moved to the single source and single receiver. The thing is, the trick is that you have to have a lot more of them to make up for the fact that you've got additional signal to noise that you have to recover that you don't get when you give up the array. But as long as you've got enough, as long as your sampling is dense enough, then it's actually preferable just to have the single source and receiver, because you get away from the array effects. Can you do that with a drone system? Well, yeah, you can. And whether you do it on the source side or whether you do it on the receiver side, it's up to you, and that depends on what your terrain is like. So we've looked at both of those options, and we think that we can get much higher trace densities with this method than we can get with manual receivers deployment.
Yeah, well, good luck. It's great technology. It'd be great to see it employed in those difficult terrains.
Yeah, thanks, Jeff.
Thank you.
Looks like Lewis Lee. Oh, sorry. Go ahead, Cal.
No, you go ahead. I saw that as well. I was going to say the same thing. So you got it.
Okay, yeah, I was just going to say it looks like we've got someone with some live sound engineering experience that may have some insight on clean signals. Louis or Lewis?
Hi, yeah. Y'all hear me?
Yeah, it's kind of quiet, but we can hear you there.
So yeah, my experience just as a live sound engineer kind of fed into my career as a geophysicist. So for us, we focus on creating the most clean signal we can in order to create a good performance, right? If you don't hear anything that's going wrong, that means I'm doing my job right. Part of doing my job right is creating the most stable sound and signal structure I can. As such, I mean, I'm responsible for understanding where I'm procuring power from. And if I'm procuring power from an unstable source, i.e. like, bad amperage, bad voltage, bad wiring, that then translates into poor signal on stage because my mics can't get powered properly. And I believe that there's a small cross section here of EM and signaling just on the fact that where we procure our drones and where we procure our items and how it's built from the ground up really influences our signaling as a whole.
Yeah, do you ever run across, whoops, am I still on? Yeah. Oh. You ever run across twisting the cabling to reduce the noise?
Part of it, when we store cabling, we do an over-under technique to help preserve cables. But in terms of twisting and rotating cables, is usually we're more concerned with crossing power lines and signal lines, and we always make it a point to cross them perpendicular to each other. And then running that's even if it's a shielded line. It's just good practice to do it shielded or not. And then we run power and signal lines parallel to the other. So all power lines are ran parallel to each other, and all signal lines ran parallel. And if they ever need to cross, we make it a very, very big point to cross perpendicular.
Gotcha.
Yeah, very interesting. I know particularly there's some research at Carleton University maybe a couple years ago that looked at the direct current effects of the DC batteries feeding into the three-phase ESCs and kind of the effect of that, which seems to make, I guess, a cloud of electromagnetic interference around the drone. So that was an interesting study. I know a little bit, not dealing with the high frequency stuff, but just kind of the DC noise that is produced by the drones, and it was a pretty interesting study there, and it touched on some of that stuff. So
that's pretty interesting, Cal. Can you maybe send a little reference in the chat down there if you can think of the title?
Yeah, no, I can definitely send the DOI or whatever in the chat. Just give me a sec here. Gary, I saw your hand was up earlier. I don't know if you had a question or something, or if you wanted to contribute. I just wanted to make sure we're not missing you.
Okay, thanks. No, I just wanted, I have a comment for John Archer. This is such a cool idea that you're working on. I can't imagine that some of the big companies that have in-house researchers aren't already working on this. At one time early in my career, I worked for the upstream research lab at Exxon, and this is the kind of thing that those guys would have already been doing. Although these days I have no idea what their approach to the market is, but I would say that, you know, don't give up hope that somebody's looking at this, because even in the areas where we're producing shale, I think they're still doing seismic for both exploration and monitoring of the activities out there. So some of the stuff you're doing could still be useful.
Yeah, I appreciate that, Gary. Yeah, I think there are people out there, and you know, one of my goals is to try and get it out to people that this isn't a closed system, that we're at the stage now where, okay, Total are no longer investing in it, but it's still available. We just finished something, we're at the point we're ready to go to the next stage, and we're looking for someone who's willing to come along and if not fund all of it, at least fund part of it. It would be a real shame, as you say, to stop at this point when I think most of the hard work is done.
Yeah, the problem is this kind of effort is going to have to take the money that you can earn from an oil and gas kind of operation in order to be able to fund the research, because it's just the logistics and the research are just too high.
That's right. It's definitely, it's a big budget, but we're not that far away. You know, really, realistically, I think we're a couple of years away from having something which is commercial at this point.
Well, good luck with it.
Thank you.
Yeah, John, and I see that the kind of the swarm maintenance, you know, stuff that you've got along with the app could be its own thing right there. You know, not even thinking about the darts coming down or anything like that, but just from a safety standpoint and from a user standpoint, if anyone for any reason wants to have a drone, more than one drone out collecting data of any kind, you know, that's seems like you've got a pretty good system developed there.
Yeah, and I'd point you to our partners, Scallion. They're the people who developed the EasyChain software, which handles the fleeting and the collision avoidance and so on. So yeah, they did a great job for us on that. Then the command and control, we're actually looking at continuing on with development of that, because there's a lot that we could use it for, even if it's just, you know, it's quite cool being able to track people with an update rate of a few seconds anywhere they are in the world without needing to have a cell phone tower nearby, because as you guys know, some of the places we work are a long way away from infrastructure. And if you can just put up your own little LoRa antenna and then know where everybody is, then, you know, that's a nice little spin-off just on its own. So I definitely think some parts of it will move on, but, you know, I'd really like to see the whole thing go forwards.
John, if I could add to that, I was just curious, was there a pilot in the loop for each drone in the operation?
Yeah, there was a pilot in the loop for each drone in the operation, which obviously is not sustainable going forwards. But that's because right now the AI is still in the learning phase. You know, we really need to get a huge amount of information, and that's just going to come by doing more and more surveys and getting more imagery from above, and keep training it. And then once the AI is at a point where it's at a certain level of accuracy, then we can start to remove the pilots from the loop, and then have gradually fewer and fewer pilots controlling more and more drones.
So then, assuming this project could continue forward, in your opinion, how many years off do you think we are from that?
I think that, well, the drone we have at the moment is a prototype, and I think it needs to go to the next stage. So, you know, one thing we noticed is that the refueling was incredibly inefficient. It took 2 guys to refuel, to change the batteries. It's all fiddly. It takes 2.5 minutes to refuel. So most of the inefficiency in the production was in the refueling. So the first thing we're really looking at is, you know, let's have quick quick connect batteries, and then we can make the whole thing automated with, you know, industrial robots to be swapping those batteries in and out. And you can really start to get some production and also remove people from the loop. That's not a big deal because all that stuff exists. It's just a case of putting it together. It's all stuff that's out there, and we just need to basically incorporate it. We're not reinventing anything. And then the same thing again with the darts. The darts are too big. We want to get them a lot smaller. We want to move away from geophones and go to accelerometers. All of that makes them smaller and lighter, which allows us to carry more of them, which gives us more range, you know, and everything kind of snowballs and gets more cost effective. But as you say, and I think we've done let's say Total has done the hardest part, because getting that certification from the DGAC was not easy. And now they've got that. I think from that point on, it makes future certifications a lot simpler, because you've already got your ConOps in place and you've done your SORA methodology. And now we just have to start to make it more and more robust and work on it.
Excellent. Thank you.
Great, thank you for that excellent discussion there. I would like to ask anyone else if they have any final questions to unmute themselves and ask, or fire them into the Q&A, and especially take this time right now to thank all of our wonderful presenters today. Everyone did an amazing job presenting what they've been working on, and I was really pleased to see everything that has gone on today. It's truly amazing seeing all of this stuff. So
I've got one question for Jamie, if he's still on. I noticed in the some of the videos, it looked like the charcoal was coming out of the balloon. Is that something that, does that affect, you know, does that slowly bring the balloon down over time throughout the day? And Jamie may have stepped away from the computer. I think he's still on, but anyway, if he pops back up, well, maybe I'll just hit him up about it. So. Anyone else? I would like to say one more thing for Markku. Really impressed with the line kilometers that you're achieving with your UAV mag setup. It's just really neat to see that much efficiency in survey.
Yeah, I also will comment on that. It's pretty remarkable, because that's kind of the ideal that we would love to have, say, here in Canada, and I'm not sure what the current regulations are kind of elsewhere in the world, because I haven't been staying on top of them, and they seem to change month to month. But yeah, getting beyond visual line of sight, or BV loss, as a lot of people have been calling it, is yeah, kind of this idea. I know moving forward there was some talks, particularly in Canada, with the jurisdiction to start trying some of these surveys, particularly in the mining industry, because we're working in relatively remote areas where there aren't too many people. So the risk is, you know, the biggest risk would be crashing your drone and probably starting a forest fire or something like that if you're in BC. But until you know, we get some flights and kind of building off of John's talk of really demonstrating, you know, the engineering into this in terms of systems and showing the safety, I think they're going to be pretty hesitant to yeah, move forward with the regulations until someone can kind of take the reins there and do that. So I'm looking forward to that into the future, because yeah, the benefits of just being able to send something up for 5 hours and not have to constantly change batteries and do this out in the middle of the cold for half the season, here in Canada, it would be amazing.
I agree. And I think there was a question earlier that may not have been answered, but it was for John Himes regarding the resin he used to 3D print parts for his drone. Did you see that earlier, John?
It looks like Himes is going to answer that. I would like to add to what Callum was saying there. Frankly, a lot of what you see with Transport Canada, they like those who have proven the BVLOS operation outside of Canada, and then bring it here native. So, yeah.
Yeah, that's really interesting, because I haven't been too up on the regulations lately with that, but that's something interesting to see. Someone who's done it elsewhere and then be able to demonstrate that and then bring it here. I think that yeah, might be a good way to move forward with it. Thank you for that. Alrighty, well, if there isn't any more questions that anyone has or comments or anything like that, I think we're getting close to the hour here, so last chance to add anything into the discussions today if you would like to. If not, I think we'll be looking to sign off here, and we can look forward to tomorrow, the exact same kind of schedule. I believe we have talks tomorrow that are on gamma ray spectroscopy from drones, as well as gravity, and some guidelines talks too that everyone can be looking forward to. And I think at the end of the day tomorrow, what we're going to do is have the same sort of open discussion format, and if anyone has any questions from throughout the entire conference, we'll also be looking to facilitate that. So if you wake up in the night and have a burning question, write it down, and we'd be happy to answer and have some more discussion then. So with that, if there isn't any more comments or questions, I think we can sign off here, and thank you once again, everyone, for joining us today. This has been another great day of presentations and discussions, and I look forward to our final day tomorrow.